Is the universe finite? This ancient and profound question, once the exclusive domain of priests and philosophers, was taken up in the modern era by a new kind of explorer. These were not the navigators and cartographers who charted the Earth's oceans and continents, but the celestial geographers, the telescope innovators who, for the first time, began to map the true scale and structure of the cosmos. The foremost of these was William Herschel, a German musician who had defected to England during the 7 Years' War. Herschel was a man of extraordinary diligence and polymathic talent. By day, he was a celebrated composer and performer. But his true passion was the night sky. He constructed his own telescopes, grinding and polishing the mirrors with the same meticulous precision that he applied to the crafting of his cellos and oboes. Each of his instruments was a masterpiece, not just of optics, but of artistry, with intricate inlays and polished brass fittings. To possess a Herschel telescope today is akin to possessing a Stradivarius violin, but they are far rarer, accompanied by his sister Caroline, a brilliant astronomer in her own right. Herschel would spend every clear night systematically sweeping the heavens, charting the positions and brightness of thousands of stars. He gained international fame in 1781 with the discovery of the planet Uranus, the first new planet to be identified since antiquity. This notoriety secured him a royal stipend, which freed him to pursue his astronomical passions full-time. Herschel developed a method for gauging the relative distances to stars based on their apparent brightness, a technique he called stargazing. By counting the number of stars in different directions, he built the first ever map of our own galaxy, the Milky Way. He envisioned it as a vast, flattened, disc-like arrangement of stars, a grindstone in shape, with our own solar system situated somewhere near its center. He was also the first to systematically catalog the hundreds of faint, fuzzy patches of light he called nebulae, the nature of which would remain a deep and contentious mystery for the next century and a half. Herschel's universe was a vast, planar island of stars, but the question of what, if anything, lay beyond its shores remained unanswered. The quest to build ever larger and more powerful telescopes was the driving force of 19th-century astronomy. Herschel's largest telescope, with its 40-foot tube, remained the biggest in the world for over half a century. But it was eventually surpassed by the Leviathan of Parsonstown, a colossal instrument built in the 1840s by William Parsons, the 3rd Earl of Ross, on his estate in the green, and often rainy, heart of Ireland. The Leviathan was an engineering marvel, with a 6-foot diameter mirror and a 60-foot-long tube, maneuvered by a complex and cumbersome system of cables, pulleys, and cranes. The damp Irish climate was far from ideal for astronomy. Parsons famously quipped that when his telescope was visible, rain was imminent, and when it was obscured, it was already raining. But on the rare, clear nights, the Leviathan's immense light-gathering power allowed it to see what no telescope had seen before. When Lord Rosse turned his great eye to the nebulae catalogued by Herschel, he was the first to discern their true and astonishing structure. Many of them, he saw, had a distinct spiral form, like cosmic whirlpools. This discovery led Rosse to revive a speculative idea that had been proposed a century earlier by the German philosopher Immanuel Kant, that these spiral nebulae were not clouds of gas within our own Milky Way, but were, in fact, distant island universes, vast, independent galaxies of stars, just like our own. This was a breathtaking and revolutionary idea, one that, if true, would expand the scale of the known universe by a factor of millions. But the evidence was still circumstantial. And the debate between the island universe hypothesis and the more conventional view of the nebula as nearby, star-forming regions would rage for another 75 years. In the meantime, 2 other crucial advances were made in the mid-19th century. The first was the refinement of telescope optics to the point where the sharpness of an image was no longer limited by the quality of the mirror, but by the unavoidable blurring effect of the Earth's turbulent atmosphere. This new level of precision enabled the second, and more profound, breakthrough, the first successful measurement of stellar parallax. Parallax is the small apparent shift in the position of a nearby star against the background of more distant stars as the Earth orbits the Sun. It is the same effect you see when you hold your finger out at arm's length and look at it first with one eye, and then the other. The apparent shift of your finger against the distant background is a parallax shift. For centuries, astronomers had tried and failed to detect this effect for the stars. The fact that the shift was so small, so immeasurably tiny, was a powerful argument for the immense distances to the stars. Finally, in the 1830s, Friedrich Bessel and others succeeded. By measuring this minuscule angular displacement and using the simple geometry of triangulation, astronomers could, for the first time, directly calculate the distances to the nearest stars. The results were staggering. Even the closest stars were trillions of miles away, their light taking years to reach us. Combined with Herschel's stargazing, which showed that the Milky Way extended for thousands of times this distance, it became clear that our own galaxy was an island of almost unimaginable proportions, a realm of trillions of miles. The second great innovation of the 19th century was the application of photography to astronomy. Before the 1840s, an astronomer's only way of recording what they saw through the telescope was to draw it by hand. Galileo's intricate watercolor paintings of the moon are a beautiful example of this. But the human eye is a fleeting and unreliable detector, and the hand is an imperfect recorder. The invention of the photographic plate was a game changer. For the first time, astronomers had a way to create a permanent, objective, and detailed record of the night sky. But the true power of astrophotography lay in its ability to see what the human eye never could. The eye is an instantaneous detector. It cannot accumulate light over time. A photographic plate, however, can be exposed for hours, even nights, on end, slowly and patiently, gathering the faint, ancient photons from the most distant and dimmest of celestial objects. This ability to integrate light over long periods opened up a new, deep and previously invisible universe to our view. And in the early 20th century, a new and powerful instrument was being built on a mountaintop north of the then small and tranquil town of Los Angeles. An instrument that would use this new photographic power to finally solve the mystery of the spiral nebulae and to fundamentally and irrevocably change our entire conception of the cosmos. The man who would wield this instrument was a young, ambitious, and brilliantly talented astronomer named Edwin Hubble. Hubble was a true Renaissance man. Before dedicating his life to astronomy, he had been a star athlete, a heavyweight boxer, an attorney, and a Rhodes Scholar. He had an authoritative, almost aristocratic demeanor and a self-assurance that bordered on arrogance. But he also had a singular, unwavering focus, and he had set his sights on the great, unresolved question of the nebulae. The new 100-inch Hooker telescope at the Mount Wilson Observatory was, at the time, the largest and most powerful in the world, and it was the perfect tool for the job. Working with his assistant, Milton Humason, a man who had started his career as a mule driver, hauling supplies up the mountain, and had worked his way up to become one of the most skilled and respected observational astronomers of his time, Hubble began to take a series of long-exposure photographs of the Andromeda Nebula, the largest and brightest of the spirals. The photographic plates produced by Humason were legendary for their sharpness and clarity, a testament to his immense skill and patience. And on one of these plates, in 1923, Hubble found what he was looking for. He identified a number of individual stars within the nebula that were not constant in their light, but were pulsating, their brightness varying in a regular periodic way. He recognized these as Cepheid variables, a special and very important type of star. The key to the Cepheids had been discovered a decade earlier by the astronomer Henrietta Leavitt. She had shown that there was a direct and precise relationship between the period of a Cepheid's pulsation and its true intrinsic luminosity. They were standard candles, cosmic lighthouses whose true brightness could be known. Hubble could measure the period of the Cepheids in Andromeda. From Leavitt's period luminosity relation, he could calculate their true brightness, and by comparing their true brightness to their apparent brightness as seen from Earth, he could calculate their distance. The result was a number that would forever change our place in the universe. Andromeda, he calculated, was approximately 1 million light-years away, far, far outside the known boundaries of our own Milky Way. The spiral nebulae were not clouds of gas in our own backyard. They were, as Kant had speculated, immense island universes, vast, independent galaxies in their own right, each containing billions of stars. The universe was not a single galaxy. It was a universe of galaxies. The known cosmos had expanded. In a single, intellectual leap, by a factor of millions, it was a discovery that was as profound and as humbling as the Copernican revolution 4 centuries earlier. Hubble's work was not done. In the process of studying these new, distant galaxies, he would make a second discovery that was even more profound, a discovery that would reveal the dynamic and evolutionary nature of the universe itself. The foundation for this discovery had been laid a decade earlier by the astronomer Vesto Slipher, who had been painstakingly measuring the spectra of the spiral nebulae. A spectrum is created by passing the light from a celestial object through a prism or a diffraction grating, which splits the light into its constituent colors, its rainbow. Imprinted on this rainbow are a series of dark absorption lines, which correspond to the specific wavelengths of light that have been absorbed by the chemical elements in the object's atmosphere. These lines act as a unique chemical fingerprint, but Slipher had noticed something strange. The spectral lines of most of the nebulae were not at their expected laboratory wavelengths. They were systematically shifted towards the red end of the spectrum. This is a manifestation of the Doppler effect, a phenomenon that is familiar to us from the world of sound. The pitch of an ambulance siren sounds higher as it approaches you, and lower as it recedes. This is because the sound waves are compressed as the ambulance moves towards you, shortening their wavelength and increasing their frequency, and stretched as it moves away, lengthening their wavelength and decreasing their frequency. The same effect applies to light. When a light source is moving towards us, its light waves are compressed, and its spectral lines are shifted to shorter, bluer wavelengths, a blue shift. When it is moving away from us, its light waves are stretched, and its spectral lines are shifted to longer, redder wavelengths, a red shift. The amount of this shift is directly proportional to the object's velocity along our line of sight. What Slipher had found was that the vast majority of the spiral nebulae were redshifted, and therefore were moving away from us at incredible speeds. This was a deep puzzle. If the galaxies were moving randomly through space, we would expect to see roughly equal numbers of blue shifts and red shifts, as many galaxies moving towards us as away from us. But the overwhelming preponderance of redshifts suggested a systematic and universal motion of recession. At first glance, this seemed to reinstate a pre-Copernican, Earth-centered view of the cosmos. If all the galaxies are moving away from us, does that not mean that we are at the very center of the universe? But a more careful thought reveals that this is not the case. Imagine a cake with raisins in it that is being baked in an oven. As the cake expands, every raisin will see every other raisin moving away from it. The further away a raisin is, the more cake there is to expand between them, and so the faster it will appear to be receding. There is no center to this expansion. The expansion is happening everywhere. The universe is like this expanding cake. Every galaxy is moving away from every other galaxy. An observer in any galaxy would see the same universal pattern of recession. There is no special privileged center. Our galaxy is just one of many, a participant in a cosmic expansion of universal proportions. Hubble's great contribution was to combine Slipher's redshift measurements with his own, new distance measurements to the galaxies, derived from his observations of Cepheid variables, and when he plotted the velocity of the galaxies against their distance. He found a remarkable and simple relationship. The further away a galaxy is, the faster it is moving away from us. This is Hubble's law, the fundamental observational cornerstone of modern cosmology. It is the definitive proof that our universe is not static and eternal, as had been assumed for millennia, but is a dynamic, evolving, and expanding entity. Hubble himself, a cautious and conservative observer, was reluctant to embrace the full theoretical implications of his own discovery. But others, like the Belgian priest and physicist Georges Lemaitre, who had independently derived the idea of an expanding universe from Einstein's equations of general relativity, saw its profound meaning. If the universe is expanding today, then it must have been smaller, denser, and hotter in the past. If you run the movie of the cosmic expansion backwards, all the galaxies would rush back together, eventually converging to a single, infinitely hot and dense point in the distant past. This was the birth of the Big Bang theory, the idea that our universe originated in a singular cataclysmic event, a day without a yesterday, as Lemaitre poetically described it. The expanding universe revealed by Hubble's observations is a place of profound and often counterintuitive geometry. It is a universe without a center and without an edge. The question posed by the ancient Greek general Archytas, "If I reach the outermost boundary of the heavens, could I extend my staff or hand into what lies beyond?" is a question that is based on a fundamentally flawed classical intuition about the nature of space. In modern cosmology, the universe does not have a physical boundary. There is no cosmic wall where space simply ends, but there is a boundary of a different kind, a boundary of information, a cosmic horizon that is dictated by the finite age of the universe and the finite speed of light. Since the universe is approximately 13.8 billion years old, we can only see the objects whose light has had time to reach us in that time. This defines a spherical, observable universe around us. We can never know what lies beyond this horizon. The situation is made even more profound by the fact that space itself is expanding. The light from a very distant galaxy has to travel through a space that is stretching as it goes. This means that a galaxy that was, say, 13 billion light-years away when its light was emitted is now much, much further away from us. And because the expansion is accelerating, there are regions of the universe that are receding from us faster than the speed of light. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, but it does mean that the light from these regions can never, ever reach us. They are beyond our event horizon, causally disconnected from our future. They are, for all practical purposes, in a different universe. Our perception of the cosmos is fundamentally constrained. But while the universe may not have a spatial edge, it does have a temporal origin. The expanding, diffuse, and cold universe we see today is the evolved state of a much smaller, much hotter, and much denser early universe. If we run the movie of cosmic history backwards, we see the galaxies rushing back together, the space between them contracting, the temperature and the density of the universe rising, until, at a finite time in the past, everything was compressed into a single, primordial state. This is the Big Bang, the existence of stars and galaxies, with their immense, multi-billion-year lifespans, can create the illusion of an eternal, unchanging cosmos. But the cosmic pageant is not everlasting. It began in a blaze of unimaginable heat and pressure some 14 billion years ago. To understand the story of this genesis and its subsequent evolution, we need a theory of gravity. But Newton's theory, with its simple, intuitive concepts of an absolute, three-dimensional space and a universal, linear time, is not sufficient. To understand a universe where space and time are themselves dynamic, pliable entities, we need the strange and beautiful language of Albert Einstein's general theory of relativity. Einstein's theory of general relativity, published in 1916, was a revolution in our understanding of gravity, of space, and of time. It was an intellectual achievement that was as profound and as culturally significant as the artistic breakthroughs of Stravinsky or the literary innovations of James Joyce. It replaced the static, clockwork universe of Newton with a more organic, more dynamic, and far stranger reality. At the heart of general relativity is a new and radical idea. Gravity is not a force that acts in space. It is a manifestation of the curvature of space-time, by mass and energy. Imagine a stretched rubber sheet. If you place a heavy bowling ball in the center, it will create a dip, a curvature in the sheet. If you then roll a small marble nearby, it will not be pulled towards the bowling ball by some mysterious action at a distance force. It will simply follow the straightest possible path in the curved geometry of the rubber sheet, a path that will lead it to spiral in towards the bowling ball. In the same way, the sun does not exert a direct gravitational pull on the Earth. Instead, the mass of the sun curves the four-dimensional space-time around it, and the Earth, in its orbit, is simply following a geodesic, the four-dimensional equivalent of a straight line. In this curved space-time, the universe, in this picture, is not a static stage. It is a fluctuating amusement park ride, a fun house where the very walls and floor are constantly distorting and contorting in response to the distribution of matter and energy within them. Light itself is not immune to this curvature. A beam of light, as it travels through the universe, must follow the curves and the dips of space-time. This phenomenon, gravitational lensing, is one of the key predictions of general relativity, and it has been confirmed with stunning precision. The light from a distant quasar can be bent around a massive, intervening galaxy, creating multiple, distorted images of the same object. The mathematics of general relativity is notoriously complex. It is said that in the early days of the theory, only a handful of people in the world truly understood it. But its conceptual essence can be grasped through two beautifully simple, foundational ideas. The first is the principle of equivalence. Einstein was struck by a strange and unexplained coincidence in Newtonian physics: the inertial mass of an object, its resistance to being accelerated by a force, is always exactly equal to its gravitational mass, the property that determines the strength of the gravitational force it feels. Why should these two, seemingly different properties be identical? Einstein's profound insight was that this was not a coincidence, but was a sign of a deep underlying principle that the effects of gravity are locally indistinguishable from the effects of acceleration. Imagine you are in a sealed elevator, a windowless box. If the elevator is at rest on the surface of the Earth, you will feel the familiar force of gravity pulling you down. But if the same elevator were in the depths of empty space, far from any gravitational influence, and was being accelerated upwards at a rate of 9.8 meters per second squared, you would feel an identical downward force. There is no experiment you could perform inside the elevator that could distinguish between these two scenarios. Gravity and acceleration are, in this sense, equivalent. The second key concept builds on Einstein's earlier discovery from his special theory of relativity, the equivalence of mass and energy, as expressed in the famous equation, E equals mc squared. If all mass is subject to gravity, and if energy is equivalent to mass, then energy in all its forms must also be a source of gravity. And since light is a form of energy, it must both create and respond to gravitational fields. Let us return to our accelerating elevator in deep space. If you were to shine a flashlight from one side of the elevator to the other, you would see that the beam of light appears to bend downward slightly, as the floor of the elevator has accelerated upwards in the time it takes the light to cross. But by the principle of equivalence, this scenario is indistinguishable from an elevator at rest on the Earth's surface. Therefore, a beam of light must also be bent by the Earth's gravity. This prediction, that gravity deflects light, was famously confirmed during a solar eclipse in 1919, a confirmation that catapulted Einstein to global fame and cemented general relativity as our new and revolutionary theory of gravity. Einstein's theory provides the mathematical framework for understanding the history and the evolution of the expanding universe. It tells us that the total density of matter and energy in the universe determines its overall large-scale geometry. And as the universe expands, this density changes, and so does the curvature. The theory allows us to run the movie of cosmic history backwards from the vast, cold, and nearly flat universe we see today to the incredibly hot, dense, and curved universe of the first moments after the Big Bang. This idea of a hot, primordial origin, initially proposed by Lemaitre, was given a powerful boost in the 1940s when physicists like George Gamow realized that such a hot early universe should have left behind a detectable, fossilized remnant. In its first few 100,000 years, the universe was a hot, opaque plasma. As it expanded and cooled, it would have been filled with a thermal blackbody radiation, like the glow from the inside of a hot oven. As the universe continued to expand, this primordial light would have cooled, its wavelength stretched into the microwave part of the spectrum. The universe today, they predicted, should be filled with a faint, isotropic, and cold sea of microwave photons, an afterglow of the Big Bang. At the time, the technology to detect such a faint signal did not exist. But 2 decades later, in 1965, 2 engineers at Bell Labs, Arno Penzias and Robert Wilson, while trying to calibrate a new sensitive microwave antenna, inadvertently and serendipitously discovered this very signal, a persistent, low-level hiss that came from all directions in the sky. This cosmic microwave background radiation is one of the most powerful and beautiful confirmations of the Big Bang theory. The detailed maps of the CMB that we have now created, with satellites like COBE, WMAP, and Planck, are our baby pictures of the universe, snapshots of the cosmos when it was 1,000 times smaller and 1,000 times hotter than it is today. The hot Big Bang model also solved another long-standing cosmological enigma, the abundance of helium. The universe is observed to be about 25% helium by mass. Stars, in their long lifetimes, fuse hydrogen into helium. But all the stars in all the galaxies over the entire age of the universe could not have produced this much helium. The Big Bang provides the perfect explanation. In the first few minutes after the beginning, the entire universe was as hot and as dense as the core of a star. It was a cosmic-scale nuclear fusion reactor. In a brief, furious period of primordial nucleosynthesis, a quarter of the primordial hydrogen was fused into helium, along with tiny, but precisely predictable, amounts of deuterium and lithium. The observed abundances of these light elements in the oldest, most pristine parts of the universe match the predictions of the Big Bang model with stunning accuracy. This is a powerful piece of evidence, a fossil from the first 3 minutes of cosmic history. That gives us incredible confidence in our overall cosmological story. Despite the immense success of the standard Big Bang model, a number of deep and profound mysteries remain. In the 1970s, astronomers, most notably Vera Rubin, while studying the rotation of spiral galaxies, discovered a profound anomaly. The stars in the outer parts of these galaxies were orbiting far too fast. According to Newton's and Einstein's laws of gravity, they should have been flung off into intergalactic space, and the visible matter in the galaxies, the stars, the gas, the dust was simply not providing enough gravitational glue to hold them together. This led to a radical, and now widely accepted, conclusion that the galaxies are embedded in a vast, invisible halo of some new, unknown kind of matter, dark matter, that does not emit, absorb, or reflect light, but which interacts gravitationally. This is not a small correction. The accounting is stark. When we add up all the mass that is required to explain the motions of stars within galaxies and of galaxies within clusters of galaxies, we find that the visible, baryonic matter that we are made of accounts for only about 15% of the total. The other 85% is dark. We are the cosmic minority. The nature of this dark matter is one of the greatest unsolved problems in all of science. It is not made of any of the particles in our standard model. It is something new, something exotic, something that hints at a much richer and more complex subatomic world than we have yet discovered. The search for the dark matter particle through a combination of direct detection experiments deep underground, indirect detection experiments that look for the products of dark matter annihilation in space, and production experiments at particle accelerators like the Large Hadron Collider is one of the most urgent and exciting quests in modern physics. And as if one dark mystery were not enough, the discovery of the accelerating expansion of the universe in the late 1990s presented us with another, and perhaps even deeper, one dark energy. This is the mysterious, repulsive force that is driving the galaxies apart at an ever-increasing rate. And its contribution to the cosmic energy budget is even larger than that of dark matter. The modern concordance model of cosmology presents a strange and humbling picture of our universe, the ordinary, atomic matter that makes up everything we have ever seen or touched. All the planets, stars, and galaxies constitutes a mere 4 to 5% of the total energy density of the universe. Dark matter makes up about 23 to 27%, and the vast majority, some 68 to 73%, is the smooth, mysterious, and gravitationally repulsive dark energy. We live in a universe that is not only dark, but is also dominated by a force that we do not understand. Our luminous, familiar world is just a thin, fragile foam on the surface of a vast, dark, and invisible cosmic ocean. This strange, dark, and accelerating universe, as revealed by our modern observations, also presented a number of deep, theoretical puzzles that the standard Big Bang model could not explain. The smoothness and the flatness of the universe, as we have seen, required an incredible and seemingly miraculous fine-tuning of the initial conditions. This is what led to the development of the theory of cosmic inflation. The idea that the universe underwent a period of hyper-accelerated, exponential expansion in its first, fleeting moments. Inflation, driven by the energy of a quantum inflaton, field, not only solves the smoothness and flatness problems, but it also provides a natural mechanism for generating the initial seeds of cosmic structure from the quantum fluctuations of the primordial vacuum. The evidence for inflation, in the form of the specific statistical properties of the ripples in the cosmic microwave background, is now incredibly strong. Inflation has become a standard and essential part of our modern cosmological story, but inflation also has a profound and mind-altering consequence. The exponential expansion of the early universe means that the physical universe, the totality of all that exists, is vastly, perhaps infinitely, larger than our observable universe, the region from which light has had time to reach us. We are living in a small, causally connected patch of a much grander and largely inaccessible cosmic reality. And in the context of eternal inflation, our entire universe may just be one bubble in an infinite, self-reproducing multiverse, a vast, cosmic foam of other universes, each potentially with its own different physical laws. The story of our universe, as we now understand it, is a story of a journey from a state of incredible simplicity and unity to one of vast complexity and diversity. It is a story that begins with a quantum seed, a tiny fluctuation in a primordial vacuum. This seed is then inflated to astronomical proportions, creating a vast, smooth, and flat space-time. The energy of this inflation is then converted into a hot, dense soup of fundamental particles in the Big Bang. As the universe expands and cools, this simple soup begins to form more complex structures, the light elements, the first atoms, and then, under the influence of the invisible scaffolding of dark matter, the first stars and galaxies. These stars, in their fiery lives and explosive deaths, forge the heavy elements that are necessary for the formation of planets and of life. And all of this is playing out against the backdrop of a mysterious and ultimately dominant dark energy that is driving the universe towards an ever-accelerating and perhaps eternal expansion. This is a story of incredible scope, of breathtaking beauty, and of deep, enduring mystery. And it is a story that places our own human existence in a new and profoundly humbling cosmic perspective. The atoms in our bodies, the iron in our blood, the carbon in our DNA, are the recycled remnants of long-dead stars. We are, in the most literal sense, stardust. And we live on a small, fragile planet, orbiting an ordinary star, in one of hundreds of billions of galaxies, in a universe that is composed mostly of dark, mysterious substances that we do not understand. A universe that may be just one of an infinite number of others. This is the Copernican principle taken to its ultimate conclusion. We are not special, and yet we are also, in another sense, incredibly special. We are, as far as we know, the only part of the universe that has woken up, that has become aware of itself, and that has begun to piece together the long, beautiful, and mysterious story of its own origins. The quest to understand our cosmic origins and to search for our potential companions in the vastness of space is a quest that is fundamentally enabled by technology. Science is a process of extending the reach and the power of our own limited biological senses. And in the field of astronomy, the telescope has been our primary and most powerful sensory prosthesis for the past 400 years. The story of the telescope is a story of a relentless and often ingenious pursuit of greater light-gathering power and greater resolution, from Galileo's first small handheld spyglass to the giant multimeter observatories that now sit on our highest mountaintops. The basic principle has remained the same: to collect as many photons as possible from a distant celestial object and to focus them into a sharp, detailed image. The first telescopes were refractors, which use a series of glass lenses to bend and to focus the light. But lenses have their limitations. A large glass lens is incredibly heavy, and it can sag under its own weight, distorting the image. And different colors of light are bent by slightly different amounts, a phenomenon called chromatic aberration, which leads to blurry, rainbow-fringed images. This is why all modern, large, research-grade telescopes are reflectors, a design that was first invented by Isaac Newton. A reflector uses a large, curved primary mirror to gather and to focus the light. A mirror does not suffer from chromatic aberration, and it can be supported from behind, allowing for the construction of much larger apertures. The largest single-mirror telescopes in the world today have primary mirrors that are over 8 meters in diameter, larger than a typical living room. And the next generation of extremely large telescopes, now under construction, will have mirrors that are 20 to 30 meters across, giant, segmented eyes that will allow us to see the universe with a clarity and a sensitivity that was previously unimaginable. But size is not everything. The ultimate limit to the sharpness of an image from a ground-based telescope is not the size of its mirror, but the blurring effect of the Earth's turbulent atmosphere. This is why the Hubble Space Telescope, with its relatively modest 2.4-meter mirror, has been able to produce some of the most iconic and scientifically valuable images in the history of astronomy. By placing a telescope above the atmosphere, in the cold, clear vacuum of space, we can achieve a level of sharpness and clarity that is simply not possible from the ground. The power of a modern telescope is not just in its optics. It is also in its detectors. The human retina is a wonderfully sensitive detector of light, but it is also a very inefficient one, capturing only about 1% of the photons that hit it. A modern digital detector, a charge-coupled device, is a marvel of quantum engineering. It is a silicon chip that can detect nearly every single photon that strikes it, with an efficiency of close to 100%. This, combined with the ability of a telescope to integrate light over long exposures, is what allows us to see the faint, ghostly light from the most distant objects in the universe, a light that is 10 billion times fainter than what the human eye can perceive. The story of the telescope is a story of human ingenuity, of our relentless drive to see further, to see clearer, and to understand more deeply. And it is a story that is far from over. With a new generation of giant, ground-based telescopes, with powerful new space observatories like the James Webb Space Telescope, and with a whole new array of technologies that will allow us to see the universe not just in visible light, but across the entire electromagnetic spectrum, we are poised on the edge of a new era of cosmic discovery, an era that promises to be even more revolutionary and more wonderful than all that have come before. Our human sense of vision, as powerful and as precious as it is a tiny, narrow window onto the vast, rich, and largely invisible reality of the electromagnetic spectrum. The visible light that our eyes can detect, the familiar rainbow of colors from red to violet, is just a single octave in a cosmic keyboard that spans at least 35 octaves. From the long, gentle waves of radio to the short, violent blasts of gamma rays. To truly understand the universe, we have had to build new kinds of eyes, new kinds of telescopes and detectors that can perceive these other, invisible forms of light. This journey into the invisible cosmos began in the year 1800, when the great astronomer William Herschel, while experimenting with a prism, placed a thermometer just beyond the red end of the visible spectrum, in a region where there was no visible light. To his surprise, the thermometer's temperature rose, indicating the presence of an invisible, heat-carrying radiation, which we now call infrared. The following year, the German chemist Johann Ritter, inspired by Herschel's discovery, placed a piece of paper coated in silver chloride, an early form of photographic material, just beyond the violet end of the spectrum. The paper darkened, revealing the existence of another invisible radiation, which we now call ultraviolet. These were the first tentative steps into the vast, unseen landscape of the electromagnetic spectrum. The full extent of this landscape was revealed in the late 19th century, through the theoretical work of James Clerk Maxwell, who unified the phenomena of electricity and magnetism into a single, elegant theory of electromagnetism, and the experimental work of Heinrich Hertz, who first generated and detected the long wavelength radio waves that Maxwell's theory had predicted. Hertz himself, in a famous failure of imagination, declared that his new discovery was of no use whatsoever. But a young Italian inventor named Guglielmo Marconi thought otherwise, and within a few years he had harnessed these invisible waves to create the first wireless telegraph, ushering in the age of global communications. The application of these new, invisible forms of light to astronomy has been a story of one revolution after another. Radio astronomy, which began in the 1930s with the pioneering work of Karl Jansky and the backyard radio dish of the amateur Grote Reber, has revealed a universe that is invisible to our optical telescopes. It has shown us the cold, dense molecular clouds where new stars are born, the powerful jets of plasma that are being shot out from the centers of active galaxies, and the faint, ancient glow of the cosmic microwave background itself. X-ray astronomy, which had to await the dawn of the space age, as X-rays are blocked by the Earth's atmosphere, has revealed the high-energy universe, a universe of incredible violence and extremes. It has shown us the hot, million-degree gas that fills the vast spaces between galaxies in a cluster, the matter that is being torn apart as it spirals into a black hole, and the shocked, expanding remnants of supernova explosions. Each of these different windows onto the cosmos, the infrared, the ultraviolet, the radio, the X-ray, the gamma ray, has revealed a new and different facet of the universe's personality. A familiar, placid-looking galaxy in an optical image can reveal itself to be a seething cauldron of new star formation in the infrared and a site of violent, high-energy explosions in the X-ray. To truly understand a cosmic object, we must observe it across the full spectrum. This is the era of multi-wavelength astronomy, an era where we are, for the first time, beginning to see the universe in all its rich, complex, and multicolored glory. This expansion of our senses has not just been a scientific endeavor. It has also had a profound, practical impact on our lives here on Earth. The same infrared detectors that allow us to see the birth of stars are now used in night vision goggles and in thermal imaging cameras that can monitor the energy efficiency of our homes. The same X-ray telescopes that we use to study black holes are based on the same technology that is used in the medical scanners that can save our lives. The journey into the invisible cosmos is a journey that has not only expanded our intellectual horizons, but has also, in a very real and tangible way, enriched and improved our lives here on our own, small and very visible planet. The exploration of our solar system is a journey that is increasingly being undertaken not by human beings in fragile metal capsules, but by our new robotic emissaries, our sensory extensions that can travel to the most distant, the most dangerous, and the most inhospitable corners of our cosmic neighborhood. These robotic explorers, the orbiters, the landers, the rovers, are a testament to our ingenuity, our curiosity, and our ability to project our own senses and our own intelligence across the vast, empty distances of interplanetary space. They have given us a close-up, and often breathtakingly beautiful, view of all the planets, of the major moons of the gas giants, and of a growing number of asteroids and comets. They have shown us the towering volcanoes and the vast canyons of Mars, the sulfuric acid clouds and the crushing pressures of Venus, the intricate, icy landscapes of Jupiter's moon Europa, and the methane rivers and lakes of Saturn's moon Titan. They are our eyes, our ears, our hands, our chemical noses, in places that are too hot, too cold, too radioactive, or simply too far away for a human being to ever visit. The journey to another world is a long and often lonely one, And in the absence of new revolutionary propulsion technologies, the human exploration of our solar system will likely remain confined for the foreseeable future to our nearest neighbors, the Moon and Mars. But our robots are not bound by the same fragile biological constraints. They can travel for decades. They can withstand extreme environments, and they can be sent on one-way missions of discovery. This is a new paradigm of exploration, a partnership between the on-the-ground, intuitive intelligence of a future human explorer and the tireless, long duration, and wide-ranging reconnaissance of their robotic partners. This partnership is also a reflection of a deeper, and perhaps universal, evolutionary trend. Any intelligent technological species that arises on another world will likely face the same fundamental challenges of space exploration, and they will likely arrive at the same solution: the use of intelligent robotic probes to be their vanguards, their scouts, their first tentative feelers into the great unknown. The exploration of space is also a powerful and engaging story. A story that can capture the imagination of a new generation in a way that few other human endeavors can. The real-time telemetry from a Mars rover, the daily images of a new and alien landscape, the thrill of a new discovery, all of this has the feel of a grand, cosmic video game, a game in which we are all participants, exploring a new and unknown world through the eyes of our robotic avatar. But our senses are not limited to the electromagnetic spectrum. In the last few years, we have opened up two completely new and revolutionary windows onto the cosmos, the windows of neutrinos and gravitational waves. Neutrinos are ethereal, ghost-like particles that are produced in the nuclear fusion reactions in the core of the Sun and in other, more violent, cosmic events like supernova explosions. They interact so weakly with normal matter that trillions of them are passing through your body every second without you ever noticing. To detect them, scientists have had to build detectors of almost unimaginable scale, like the Ice Cube Observatory, which has turned a cubic kilometer of the pristine, clear ice at the South Pole into a giant neutrino telescope, by detecting the faint flashes of light that are produced when a rare neutrino interacts with an ice molecule. We can begin to do neutrino astronomy, to look directly into the fiery nuclear heart of our own sun, and to see the universe in a completely new and different way. Gravitational waves, the faint ripples in the fabric of space-time itself, are an even newer and more profound sense. First predicted by Einstein a century ago, they are generated by the most violent and cataclysmic events in the cosmos: the collision of two black holes, the merger of two neutron stars, the Laser Interferometer, Gravitational Wave Observatory, and its international partners have, in the last few years, made the first historic detections of these cosmic tremors. This has opened the era of gravitational wave astronomy, a way of listening to the universe, of hearing the cosmic symphony of colliding black holes and dying stars. This is a true revolution. We are no longer like a deaf person who can only see the lightning flash of a distant storm. We can now also hear the thunder. And in the future, with space-based gravitational wave detectors like LISA, we may be able to hear the faint, primordial hum of the gravitational waves from the Big Bang itself. A sound that has been traveling towards us, unheard, for 14 billion years. The expansion of our senses, from the single octave of visible light to the vast, multimodal sensorium of modern, multi-messenger astronomy, is a testament to the relentless and beautiful human desire to see more, to hear more, to know more. And in this expansion of our perception, we are not just discovering a new universe, we are, in a very real sense, creating a new, more intimate and more profound relationship with the cosmos we all call home. The modern scientific understanding of our place in the cosmos is a story of a series of profound, and often unsettling, decenterings, For millennia, we lived in a comforting but ultimately illusory geocentric universe, a small, enclosed world with a stable, stationary Earth at its center. We were the protagonists of the cosmic drama, the special creations for whom the entire universe was made. Copernicus, Galileo, and Newton shattered this illusion, demoting the Earth to just one of several planets orbiting an ordinary star. But even in the Newtonian universe, our sun was still at the center of our galaxy. And our galaxy was, for all practical purposes, the entire universe. It was Hubble who delivered the final and perhaps most profound of these decenterings. He showed us that our galaxy is just one of hundreds of billions of others, scattered across a vast and expanding cosmic ocean. And our sun is just an ordinary G-type star, orbiting in the quiet suburbs of this ordinary spiral galaxy. There is nothing special about our position in space. And the Copernican principle, the idea that we do not occupy a privileged position in the universe, is now a cornerstone of modern cosmology. But the reality is even more disconcerting than this simple statement of mediocrity would suggest. We are not just in an ordinary place, we are in a state of constant and complex motion. The very concepts of up and down, which seem so absolute to us, are just local, conventional constructs of the Earth's gravity. Our thin, fragile atmosphere, a layer that is thinner, in relative terms, than the skin of an apple, quickly gives way to the cold, lifeless vacuum of space, a space that is just a few degrees above absolute zero. The Earth itself is spinning on its axis at about 1,000 miles per hour at the equator. It is revolving around the Sun at about 70,000 miles per hour. The Sun, in turn, is orbiting the center of the Milky Way galaxy at about 500,000 miles per hour, completing one great galactic year every 225 million years, and the Milky Way itself is not stationary. It is gravitationally bound to its large neighbor, the Andromeda Galaxy. And the two of them, along with a few dozen smaller satellite galaxies, are falling towards the Great Virgo cluster of galaxies at about 1,000,000 miles per hour. And this entire vast supercluster of galaxies is itself in motion, part of a great cosmic flow towards an even larger concentration of mass known as the Great Attractor. To contemplate your true position and motion in space is a dizzying and deeply unsettling existential experience. It is to be stripped of all our familiar terrestrial anchors, to be confronted with the profound and beautiful truth of our own. Cosmic homelessness. We are not at rest. We are in a state of perpetual, multi-layered, free fall through the vast, dark, and expanding universe. It is perhaps a good thing that our astronauts are, for the most part, disciplined test pilots and technically minded engineers. If NASA were to send a poet or an artist into space, they might be so profoundly and existentially overwhelmed by this experience of radical decentering that they would be unable to function. Our everyday terrestrial intuition is a poor guide to the true, and often terrifying, scales of the cosmos. To grapple with the immense and often unimaginable scales of space and time, we must resort to the use of scale models and analogies. But even these can only take us so far. Imagine we want to build a scale model of our solar system. If we shrink the Earth down to the size of a golf ball, about 4 centimeters in diameter, then the Moon would be a small pea, orbiting about an arm's length away. Mars would be a gumball, at its closest approach about 800 feet away. And Jupiter, the king of the planets, would be a beach ball, about 1.5 miles away. The Sun, in this model, would be a luminous, glowing sphere, 14 feet in diameter, about 1/3 of a mile away. The entire solar system, out to the orbit of Pluto, would be a small town, about 12 miles across. So far, so good. We are dealing with familiar, human-scale objects and distances, but this is where our intuition begins to break down. In In this same scale model, where our entire solar system is the size of a small town, where is the nearest star? It is not in the next town over, or even in the next state. The nearest star, Proxima Centauri, would be over 13,000 miles away. If our solar system is a single town, then the average distance between towns in our galaxy is so vast that the entire surface of the Earth would contain only one of them. The emptiness of space is almost impossible to comprehend. This same scale factor also allows us to visualize the speed of light, which in our everyday experience seems to be instantaneous, would, in this model, be slowed down to a leisurely walking pace, about 1 meter per second. At this speed, it would take light 8 minutes to walk from the sun to the Earth. It would take it 5 hours to walk across our small 12-mile-wide town of a solar system. But to walk to the nearest star, to the next town over, would be a journey of 4.5 years, a continuous, non-stop circumnavigation of the entire Earth. This is why when we look at the stars, we are looking back in time. We see the sun as it was 8 minutes ago. We see Proxima Centauri as it was over 4 years ago. The question, what is happening in the universe right now, is a meaningless one. Light is the fastest messenger we have, and its speed is finite. Our perception of the universe is always and irreducibly a perception of its past. To visualize the scale of the universe of galaxies, we need to apply a second, equally massive, reduction factor if we now shrink our entire house-sized Milky Way galaxy down to the size of a single atom. Then the average distance between galaxies would be about 3 millimeters. The entire observable universe, in this model, would be about the size of the Earth. But even this analogy fails, because it presents a static, snapshot view. The reality is that we are seeing the different parts of this Earth-sized universe at different times in their history. We are seeing the other side of our own. Atomic Milky Way as it was 20,000 years ago. We are seeing the nearest. Atomic galaxies as they were a few million years ago, and we are seeing the most distant atomic galaxies on the very edge of our observable Earth, as they were over 13 billion years ago when they were just forming. We are not looking out at a universe. We are looking out at a history. We are constrained not just by space, but by time. Another powerful way to visualize our place in cosmic history is to compress the entire 13.7 billion-year lifespan of the universe into a single, familiar, human calendar year. In this cosmic calendar, the Big Bang happens at the first instant of January 1st. Our own Milky Way galaxy begins to form in late February. The spring and the summer are a long, slow period of galactic evolution, of the birth and the death of generations of stars. Our own solar system does not even begin to form until early September, about 2/3 of the way through the cosmic year. The Earth is formed a couple of days later, and the first, primitive, microbial life appears on our planet within a week or two. For the next 3 months, all of October, all of November, and the first half of December, life on Earth remains almost entirely microscopic. There are no plants, no animals, no creatures larger than a single cell. The tempo of evolution begins to accelerate in mid-December with the Cambrian explosion of diverse, multicellular life in the oceans. The dinosaurs appear around Christmas, and they rule the Earth for a few glorious days until they are wiped out by a massive asteroid impact on December 30th. The first hominids, our distant bipedal ancestors, do not appear until the evening of New Year's Eve, about 3 hours before midnight, and the entire span of recorded human history, from the first cities and the invention of writing to the present day, takes place in the final 20 seconds of the cosmic year. The Copernican revolution happens 1 second before midnight. Your own entire lifespan is a tiny fraction of that final second. This perspective is a powerful and deeply humbling one. It shows us that we are the newest of newcomers to the cosmic stage, the product of a long, slow, and often contingent evolutionary history. But it also opens up a vast and tantalizing space for speculation. If our own Earth-like planet formed in early September of the cosmic year, it is entirely plausible that other similar planets could have formed much earlier, perhaps in June or July. If life and intelligence were to evolve on such a planet at a similar rate as they did on Earth, then an extraterrestrial civilization could have reached our current level of technological sophistication by late September, at the very time when the first simple life was just beginning to stir in the oceans of our own young planet. What would such a civilization, with a 4 billion-year head start on us, be capable of? It is a thought that is both inspiring and deeply unsettling. We are living at a remarkable and perhaps perilous threshold in our own technological evolution. The last tenth of a second of the cosmic year has seen the birth of computers, of space travel, of genetic engineering, of the internet. The pace of change is accelerating at an exponential rate, making any confident predictions about our own long-term future an exercise in futility. The recognition of our own profound temporal and spatial mediocrity, of our smallness in the vast sweep of cosmic time and space, is a double-edged sword. It can be a source of existential anxiety, but it can also be a source of immense inspiration, a call to recognize our own vast potential as a young and just awakening, self-aware species. And it fuels the deep and enduring hope that if we are not unique, if the same processes that led to our own existence have played out on countless other worlds, then the cosmos must be an exceedingly interesting and perhaps a wonderfully populated place. The modern scientific search for life beyond Earth, the field of astrobiology, is a young and profoundly interdisciplinary endeavor. It is a field that could not have come into being until a number of other foundational sciences had reached a certain level of maturity. Speculation about extraterrestrial life has existed for millennia, from the atomists of ancient Greece to the Renaissance philosopher Giordano Bruno, who was burned at the stake for his heretical belief in a plurality of worlds. But these were, for the most part, philosophical and imaginative conjectures, untethered to any empirical evidence. The birth of astrobiology as a true scientific pursuit in the mid-20th century required the convergence of a number of different and previously separate lines of inquiry. One of the most fundamental of these was chemistry. The modern science of chemistry began in the late 18th century with the work of Antoine Lavoisier, who established the concept of the chemical element and the law of conservation of mass. In the early 19th century, John Dalton revived the ancient Greek idea of atoms, placing it on a firm, quantitative footing and establishing the principles by which elements combine to form compounds. By the mid-19th century, the periodic table had been discovered, providing a deep organizing framework for understanding the properties and the relationships of all the known elements. The application of this new chemical knowledge to the stars was made possible by the development of spectroscopy. In 1814, the German optician Joseph von Fraunhofer discovered a series of dark lines in the spectrum of the sun, lines that were later understood to be the unique absorption fingerprints of the different chemical elements in the sun's atmosphere. This was a revolutionary breakthrough. For the first time, we could determine the chemical composition of a distant celestial object without ever having to leave the Earth. And what we found was a profound and beautiful truth. The chemistry of the cosmos is universal. The same elements that we find on Earth are also found in the sun, in the distant stars, in the galaxies. While their relative abundances are different, the universe is overwhelmingly composed of hydrogen and helium. The fundamental building blocks are the same everywhere. The 20th century heralded the birth of cosmic chemistry, the understanding of how these elements are created. The light elements, hydrogen and helium, were forged in the first few minutes of the Big Bang. All the other, heavier elements, the elements that are essential for the formation of rocky planets and for the chemistry of life, the carbon, the nitrogen, the oxygen, the silicon, the iron, were created in the nuclear furnaces of stars and then scattered throughout the galaxy in the spectacular, explosive deaths of these stars as supernovae. We are, as the astronomer Carl Sagan famously said, made of star stuff. The atoms in our bodies have a long and dramatic cosmic history, a history of stellar birth and death that stretches back for billions of years. This universality of chemistry is one of the foundational pillars of astrobiology. It tells us that the raw materials for life, the biogenic elements like carbon, hydrogen, nitrogen, and oxygen, are not rare or exotic, but are among the most abundant elements in the universe, after hydrogen and helium. The ubiquitous presence of these elements, and of water, throughout the cosmos is the primary reason that most scientists believe that life is not a unique terrestrial phenomenon, but is likely to be a widespread and common feature of the universe. The second great scientific pillar upon which astrobiology is built is, of course, biology itself. The invention of the microscope in the 17th century, a contemporary of the telescope, opened up a new and previously invisible world, a world of teeming, microscopic life, the work of pioneers like Robert Hooke, who first coined the term cell, and Antonie van Leeuwenhoek, who was the first to see bacteria and other single-celled organisms, revealed that the world was far more alive and far more complex than had ever been imagined for centuries. The question of the origin of life was dominated by the idea of spontaneous generation, the belief that life could arise directly from inanimate matter. But in the mid-19th century, the elegant and rigorous experiments of Louis Pasteur finally laid this idea to rest, establishing the principle that all life comes from pre-existing life. At the same time, the Augustinian monk Gregor Mendel was quietly laying the foundations for the new science of genetics, elucidating the fundamental laws of heredity. And then, in 1859, Charles Darwin published his monumental On the Origin of Species, a book that would forever change our understanding of life. Darwin provided a powerful and persuasive mechanism for the diversity and the complexity of the living world, evolution by natural selection. He showed how the simple and observable facts of variation, of inheritance, and of differential survival could, over the vast sweep of geological time, give rise to all the beautiful and wonderfully adapted forms of life we see around us. Darwin himself, in a famous letter, speculated about the origin of life itself, imagining a warm little pond where the first simple life forms might have emerged from a soup of basic chemical ingredients. But it was not until the 1920s that the Russian biochemist Alexander Oparin and the British geneticist J.B.S. Haldane independently developed the first modern scientific hypothesis for the abiogenesis, the origin of life from non-life. They proposed that the early Earth had a reducing atmosphere, rich in molecules like methane and ammonia, and that the energy from lightning and from the sun's ultraviolet radiation could have driven the synthesis of more complex organic molecules, like amino acids, in the primordial oceans. This primordial soup would have become a rich chemical laboratory, from which the first, simple, self-replicating molecules, and eventually the first cells, could have emerged. This was a bold and testable hypothesis, and in 1953 the American chemists Stanley Miller and Harold Urey put it to the test. In a now famous experiment, they created a sealed glass apparatus containing a mixture of gases that was thought to simulate the early Earth's atmosphere, and they passed an electrical spark through it to simulate lightning. After just a few weeks, they were astonished to find that the water in the flask had turned into a thick, brown, organic sludge, a sludge that contained a number of different amino acids, the fundamental building blocks of proteins. The Miller-Urey experiment was a landmark achievement. It demonstrated, for the first time, that the complex organic molecules of life could be synthesized from simple, inorganic ingredients under plausible, prebiotic conditions. It was a proof of principle, a demonstration that the gap between the non-living and the living was not an unbridgeable chasm, but was, perhaps, a series of small and chemically plausible steps. The third and final piece of the astrobiological puzzle was the realization of the true, vast scale of the cosmos and the dawning understanding that our own life-bearing planet was not a unique object, but was likely just one of billions of similar worlds scattered throughout our galaxy. The concept of other inhabited worlds had been a part of Western thought since the ancient Greeks, but it was not until the astronomical discoveries of the 19th and 20th centuries that this idea could be placed on a firm scientific footing. The immense distances to the stars, as revealed by parallax measurements, and the discovery of the universe of galaxies by Hubble, created a cosmic landscape of almost unimaginable vastness. The sheer number of stars in our own galaxy, now estimated to be in the hundreds of billions, made it seem almost statistically inevitable that some of them would have planets, and that some of those planets would have the right conditions for life. The great challenge was to actually detect these distant worlds. An exoplanet is a tiny, faint object, orbiting a star that is billions of times brighter. Directly imaging such a planet is an incredible technological challenge, like trying to see a firefly next to a searchlight from a distance of thousands of miles. For decades, the search for exoplanets was a frustrating and largely fruitless endeavor. But in the 1990s, with the development of new, more sensitive detection techniques, like the radial velocity method, which looks for the tiny gravitational wobble that an orbiting planet induces in its host star, the first exoplanets were finally discovered. And then, in the 2000s, with the launch of space telescopes like Kepler and TESS, which were specifically designed to search for the tiny dip in a star's light that occurs when a planet transits in front of it. The floodgates opened. We have now discovered over 5,000 confirmed exoplanets, and the number is growing every day. And what we are finding is a stunning and beautiful diversity of worlds, hot Jupiters, super-Earths, mini-Neptunes, and, most excitingly, a growing number of small, rocky, and potentially habitable worlds orbiting in the Goldilocks zone of their stars, the region where temperatures are just right for liquid water to exist on a planet's surface. The convergence of these three great scientific narratives, the universality of chemistry, the understanding of the origins and evolution of life on Earth, and the discovery of the vast and planet-rich nature of the cosmos is what gave birth to the modern science of astrobiology. It is a field that is still in its infancy, a field that is still grappling with the most profound and difficult of all scientific questions. But it is also a field that is poised on the edge of a new era of discovery, an era where we may, for the first time in human history, finally find the answer to the ancient and enduring question, are we alone? The journey to understand the origin of life on Earth is a journey into deep time, a temporal landscape that is as vast and as alien to our everyday experience as the spatial landscape of the cosmos. To navigate this landscape, to read the story that is written in the ancient rocks of our planet, scientists have had to develop a new kind of clock, a clock that is not based on the familiar cycles of the sun and the moon, but on the slow, steady, and inexorable decay of radioactive atoms. The principle of radiometric dating is beautifully simple. Certain, unstable isotopes of elements, the parent atoms, decay into other, more stable, daughter atoms at a predictable, and constant rate. This rate is characterized by the half-life, the time it takes for half of a sample of parent atoms to decay. For example, the isotope uranium-238 decays into lead-206 with a half-life of about 4.5 billion years. By measuring the ratio of parent-to-daughter atoms in a rock sample and knowing the half-life, geologists can calculate the age of the rock with incredible precision. The nucleus of an atom is a tiny, impregnable fortress. Its decay rate governed by the powerful, strong nuclear force, and it is completely impervious to the chemical and physical conditions of its environment. The half-life of a uranium atom is the same in a rock deep within the Earth's mantle as it is in a meteorite in the cold vacuum of space. This makes radioactive isotopes the perfect and most reliable clocks for measuring the immense geological timescales of our planet's history. And what these clocks have told us is a story of incredible antiquity. By dating the oldest rocks on Earth, and, even more reliably, the pristine, unaltered meteorites that are the leftover building blocks of our solar system, we have determined the age of the Earth to be approximately 4.54 billion years. With this timeline in place, we can begin to search for the first faint traces of life in the geological record. This is a challenging task, a form of cosmic detective work. For most of Earth's history, life was purely microscopic, and it left behind no obvious, bony fossils. Instead, we must search for the more subtle, indirect evidence of its existence. One of the most powerful of these are stromatolites, layered, cabbage-like rock structures that are formed by the slow, layer-by-layer growth of microbial mats in shallow, sunlit waters. Modern stromatolites are still being formed today in a few rare, hypersaline environments like Shark Bay in Western Australia. And ancient fossilized stromatolites have been found in some of the oldest sedimentary rocks on Earth, dating back as far as 3.5 billion years. These are not the fossilized organisms themselves, but the trace fossils of their activity, the fossilized remnants of the cities they built. We can also search for molecular fossils or biomarkers, the preserved chemical remnants of specific biological molecules. For example, certain complex carbon-based molecules, like steranes, are only known to be produced by complex eukaryotic cells. Finding these molecules in ancient rocks can provide a powerful chemical fingerprint of a particular kind of life. And for the very oldest rocks that have been so heated and compressed that any structural or molecular fossils have been destroyed, we can turn to isotopic tracers. Life has a subtle but detectable preference for the lighter isotope of carbon, carbon-12 over its heavier cousin, carbon-13. This is because the enzymes that are involved in photosynthesis and other metabolic processes work slightly more efficiently with the lighter isotope. This means that organic matter that has been processed by life is slightly, but measurably, enriched in carbon-12. By measuring the ratio of carbon-12 to carbon-13 in the tiny flecks of graphite that are found in the oldest sedimentary rocks on Earth, like the 3.8 billion-year-old rocks from Isua in Greenland, we can search for the faint, isotopic echo of ancient metabolic activity. The evidence from all of these different lines of inquiry, from the structural to the molecular to the isotopic, is all pointing towards the same astonishing conclusion that life on Earth began very early and very quickly. The first tentative evidence for life appears in the geological record almost as soon as the Earth had cooled down enough from its violent, fiery birth to have a stable crust and liquid water oceans. It seems that as soon as the conditions were right, life did not just appear. It exploded, gripping the young planet like a fever. This has profound implications for the search for life elsewhere. If life could arise so quickly and so robustly on our own, young, and inhospitable planet, then it seems almost inevitable that the same creative process has played out on countless other similar worlds scattered throughout the vastness of the cosmos. The journey from a simple, prebiotic soup of organic molecules to the first living, self-replicating cell is one of the greatest and most profound mysteries in all of science. It is a journey that likely took place in the first few 100 million years of Earth's history. A dark age for which we have no direct geological or fossil evidence. To understand this crucial transition, scientists must work forward, not from the evidence, but from the principles of chemistry and physics, trying to reconstruct a plausible, step-by-step pathway from the non-living to the living. This is the field of prebiotic chemistry, and it is a field that is full of both immense challenges and exciting. Recent breakthroughs. The first step, as we have seen, is the synthesis of the basic molecular building blocks of life, the amino acids, the nucleotides, the sugars, the lipids. The Miller-Urey experiment showed that these can be formed from simple, inorganic precursors in a reducing atmosphere. And while we now believe that the early Earth's atmosphere was likely not as reducing as the one Miller and Urey used, we have also discovered a host of other plausible environments for prebiotic synthesis. The hot, chemical-rich water of deep-sea hydrothermal vents, the mineral surfaces of clays in shallow, evaporating tide pools, and even the cold, icy surfaces of dust grains in interstellar space are all now considered to be viable, and perhaps even powerful, chemical laboratories for the creation of life's building blocks. And we now know that a significant fraction of the Earth's early organic inventory was likely delivered from space by the constant rain of comets and meteorites that bombarded the young planet. The universe, it seems, provided a generous, ready-made supply of the raw materials for life. But having the building blocks is one thing, assembling them into the complex, functional machinery of a cell is another. This is the jumbo jet in a scrapyard problem, the challenge of explaining how the incredible, specified complexity of life could have arisen from a random chemical chaos. The key to solving this puzzle lies in the recognition that prebiotic evolution was not a purely random process. It was a process of chemical evolution, a process of self-organization and natural selection acting at the molecular level. One of the central challenges is the chicken and egg problem of proteins and nucleic acids. In all modern life, the genetic information is stored in DNA, which is a nucleic acid, but the process of reading and replicating this information is carried out by a complex machinery of proteins. So, which came first, the information or the machinery to read it? It seems you need both to have either. The solution to this paradox is thought to lie in a hypothetical, earlier stage of life, the RNA world. RNA, ribonucleic acid, is a molecule that is very similar to DNA, but it is more versatile. It can not only store genetic information, like DNA, but it can also fold up into complex, three-dimensional shapes and act as an enzyme, a ribozyme, to catalyze chemical reactions, like a protein. In the RNA world, RNA played both roles. It was both the chicken and the egg. It was a self-replicating, catalytic molecule, a single, elegant solution to the information-function paradox. The laboratory work of scientists like Jack Szostak has provided powerful experimental support for this idea. They have been able to evolve new catalytic RNA molecules in the lab, ribozymes that can perform many of the key chemical reactions that would have been necessary for the first simple life forms. They can stitch together other RNA molecules. They can make copies of themselves. They can perform a whole host of simple metabolic reactions. The RNA world is now the leading and most well-supported hypothesis for the earliest stages of life. The final crucial step is the creation of a container, a membrane that can enclose these self-replicating molecules, protecting them from the outside world and concentrating them in a way that allows for a more efficient and more coordinated biochemistry. This is the birth of the first protocell, And here, too, nature seems to provide a surprisingly simple solution. Fatty acid molecules, which were likely abundant on the early Earth, have a hydrophilic head that is attracted to water and a hydrophobic tail that is repelled by it. When placed in water, these molecules spontaneously self-assemble into hollow, spherical structures called vesicles, with their watery heads facing outwards and their oily tails tucked inside. These vesicles are remarkably cell-like. They can grow, they can incorporate new fatty acids into their membranes, and they can even divide in a simple, physical way when they become too large. Sostock's lab has shown that these simple, fatty acid vesicles can encapsulate replicating RNA molecules, that they are permeable to the small nucleotide building blocks that the RNA needs to replicate, and that the process of RNA replication itself can drive the growth and the division of the vesicle. This is a stunning and beautiful result. It is a laboratory model of a simple, self-replicating, and evolving protocell, a system that has all the basic functional properties of a living organism. The journey from a simple organic sludge to the first, true cell was likely a long, complex, and contingent one, with many false starts and dead ends. And there are still many deep and unanswered questions. But the work of prebiotic chemists and molecular biologists is beginning to show us that this journey was not an impossible one. It was a journey that was guided by the inherent, self-organizing properties of matter, by the laws of physics and chemistry, and by the powerful creative engine of molecular, Darwinian evolution. The origin of life may not have been a single, miraculous event, but a gradual, and perhaps even inevitable, unfolding of the creative potential that is woven into the very fabric of the cosmos. The story of life on Earth is not just a story of biology. It is also a story of a deep and profoundly intimate, co-evolutionary dance between the living world and the non-living, geological and atmospheric environment of our planet. This is the central insight of the Gaia hypothesis, a powerful and often controversial idea that was first proposed by the independent scientist James Lovelock in the 1970s. Lovelock, while working for NASA on the problem of how to detect life on Mars, had a sudden, profound realization. He noticed that the atmospheres of our neighboring planets, Mars and Venus, are in a state of near chemical equilibrium. They are dead, inert, and predictable. The Earth's atmosphere, on the other hand, is in a state of wild and seemingly impossible chemical disequilibrium. It is a mixture of highly reactive gases like oxygen and methane that should, by the normal rules of chemistry, rapidly react with each other and disappear. The only reason this volatile mixture is maintained is because life itself is constantly pumping these gases into the atmosphere. The oxygen is a byproduct of photosynthesis by plants and algae. The methane is a byproduct of the metabolic activity of methanogenic bacteria. Life, Lovelock realized, is not just a passive passenger on planet Earth. It is an active, planet-scale, geological force. This led him to the Gaia hypothesis, the idea that the Earth's biosphere, atmosphere, oceans, and soils constitute a single, vast, and self-regulating system. In its weak form, the hypothesis is a relatively uncontroversial statement about the existence of complex feedback loops between the living and the non-living parts of the Earth system. In its strong and more controversial form, it proposes that the Earth itself can be viewed as a single, giant, superorganism, a living being that actively maintains the conditions on its surface to be favorable for life. Lovelock himself never claimed that this self-regulation was a conscious or a purposeful process, but he did identify a number of powerful and often surprising feedback mechanisms by which the biosphere seems to regulate the global environment. The long-term stability of the Earth's climate is one of the most striking examples. The sun's luminosity has increased by about 25 to 30% over the course of the Earth's history. By all rights, the Earth should have either frozen over in its youth or boiled away by now. And yet, the geological record shows that the Earth's average surface temperature has remained remarkably stable, within the narrow range that is required for liquid water and for life. One of the key Gaian feedback loops that is thought to be responsible for this is the carbonate-silicate cycle. Carbon dioxide, a greenhouse gas, is released into the atmosphere by volcanoes. It is then removed from the atmosphere by the slow geological process of rock weathering, where it dissolves in rainwater to form a weak carbonic acid, which then reacts with silicate rocks. The byproducts of this reaction are washed into the oceans, where marine organisms use them to build their calcium carbonate shells. When these organisms die, their shells sink to the ocean floor, forming limestone deposits and effectively sequestering the carbon dioxide from the atmosphere. The rate of this rock weathering is sensitive to temperature. When the planet gets warmer, the weathering process speeds up, pulling more carbon dioxide out of the atmosphere and cooling the planet down. When the planet gets cooler, the weathering slows down, allowing volcanic carbon dioxide to build up and to warm the planet up. It is a beautiful, planetary-scale thermostat. And life plays a crucial role in this process. The activity of soil microbes and the roots of plants significantly accelerates the rate of rock weathering, making this thermostat much more efficient and responsive. The Gaia hypothesis is a profound and deeply holistic way of seeing our planet. It encourages us to see the world not as a collection of separate, independent parts, but as a single, vast, interconnected, and co-evolving system. It tells us that we are not just living on the Earth. We are a part of the Earth, a part of its metabolism, its circulation, its consciousness. And this has deep and urgent implications for our own human activities. Our industrial civilization, with its massive release of carbon dioxide and its widespread alteration of the planet's ecosystems, is now a major and deeply destabilizing geological force. We are, in a sense, giving the Earth a fever. And while the Gaian feedback systems will, in the long run, likely restore the planet to a new, stable equilibrium, there is no guarantee that this new equilibrium will be one that is hospitable to human civilization. The Gaia hypothesis is a powerful call to a greater sense of ecological responsibility, a call to recognize our deep and intimate entanglement with the living systems of our home planet. And it is also a powerful tool for astrobiology. If life on any planet is likely to have a major transformative impact on its global environment, then one of the best ways to search for life on other worlds is to search for the signs of a planetary scale, chemical disequilibrium in their atmospheres. A planet with an atmosphere that is far from a dead, chemical equilibrium is a planet that is, in a very real sense, alive. The search for life beyond Earth is not just a search for little green men. It is a search for another Gaia. The universe is a vast and mysterious canvas, a tapestry woven from threads of light and darkness, of matter and energy, all governed by a set of fundamental rules that we are only just beginning to comprehend. For centuries, our understanding of this cosmic drama has been shaped by four primary actors: the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. These are the pillars of our physical reality, the invisible architects that build everything from the smallest subatomic particle to the largest supercluster of galaxies. But what if the stage is more crowded than we think? What if there are other hidden actors, other fundamental forces waiting in the wings, forces that have been silently shaping the cosmos in ways we have not yet even begun to imagine? This is one of the most exciting and profound questions in all of modern physics, the quest to discover a fifth force. It is a quest that has tantalized and obsessed researchers for decades, a search that could not just add a new chapter to our textbooks, but could fundamentally rewrite our entire understanding of the universe and our place within it. The clues that hint at the existence of these new forces are subtle, ghostly, and often ambiguous. They are found in the strange, anomalous behavior of the cosmos at its largest and its smallest scales. When we look out at the grand spiral galaxies, we see that their outer stars are rotating far too fast, moving with a velocity that should send them flying off into the intergalactic void if the only gravity at play was that of the visible stars and gas. This has led to the hypothesis of dark matter, an invisible but mysterious substance that seems to make up about 27% of the universe's mass energy content. But what if dark matter is not just a passive, inert substance? What if it interacts with itself, or even with us, through a new, undiscovered dark force? Such a force could explain some of the puzzling discrepancies we see in the distribution of dark matter on different scales, and it would mean that the dark sector of the universe is not just dark, but is also home to a rich and complex physics of its own. On an even grander scale, there is the mystery of dark energy, the even more enigmatic force that is causing the expansion of the universe to accelerate. A new fundamental force could be the key to understanding this cosmic anti-gravity. Perhaps a long-range, incredibly weak force that only becomes apparent over the vast, empty distances between the galaxies. The search for these new forces is not just a matter of looking out at the cosmos. It is also a matter of looking in, of probing the very heart of matter in our most powerful particle accelerators. At facilities like the Large Hadron Collider at CERN, physicists are smashing particles together at nearly the speed of light, recreating the extreme energy conditions of the first moments after the Big Bang. In the fiery debris of these collisions, they are searching for new, unexpected particles, for new, subtle interactions, for any deviation from the predictions of our current standard model of particle physics that could be the telltale signature of a new force. The implications of discovering a new fundamental force would be nothing short of revolutionary. It would be a discovery on par with the discovery of electromagnetism or the nuclear forces, a moment that would fundamentally reshape our understanding of the fabric of reality. It could provide the key to a unified theory, the long-sought dream of Einstein to unite all the forces of nature, including gravity, into a single, elegant mathematical framework. Theories like string theory, for example, naturally predict the existence of a host of new forces and particles. String theory posits that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different vibrational modes of these strings correspond to the different particles we see, and the theory requires the existence of extra hidden dimensions of space to be mathematically consistent. These extra dimensions could be the home of new forces, forces that could leak into our familiar three dimensions in subtle and potentially detectable ways. This is a vision of reality that is far richer, more complex, and more multi-layered than our current four-dimensional picture. It is a vision where the world we see is just a shadow, a projection of a much deeper, higher dimensional reality. And the quest to find a new force is, in a sense, a quest to peer into these hidden dimensions, to catch a glimpse of the true, underlying structure of the cosmos. Even our understanding of time itself could be transformed. Some speculative theories suggest that a new force could be linked to the very nature of time's arrow, the unidirectional flow from past to future. The universe is not just a stage for a fixed set of forces. It is a dynamic, evolving cosmos. And the forces of nature themselves may have changed over cosmic history. The search for a fifth force is a journey to the very frontier of our knowledge, a journey that is pushing the limits of our technology. our mathematics, and our very imagination. It is a reminder that the universe is not a closed book that we are close to finishing, but a vast, open library with an infinite number of volumes, most of which we have not even opened yet. The story of our understanding of the cosmos is a story of ever-expanding horizons, a journey that has taken us, in the span of just a few millennia, from a small, Earth-centered world to a vast 14-billion-year-old universe teeming with hundreds of billions of galaxies. This journey began with our most ancient ancestors, with the Babylonians and the Egyptians, who first looked up at the night sky not just with awe, but with a desire to understand. They were the first true astronomers, meticulously charting the motions of the stars and the planets, creating the first calendars, and laying the practical and mathematical groundwork for all that was to come. The ancient Greeks, with their unique gift for philosophical and geometrical inquiry, transformed this observational knowledge into the first comprehensive cosmological models. The geocentric model of Aristotle and Ptolemy, with its elegant, if complex, system of nested crystalline spheres, was a monumental intellectual achievement. A picture of the universe that would dominate Western thought for over 1,000 years. The Islamic world, during the long European Middle Ages, became the custodian and the innovator of this classical knowledge. Astronomers like al-Sufi and al-Battani not only preserved and translated the great works of the Greeks, but they also made their own. Crucial contributions, developing new mathematical techniques, building more precise instruments, and making new observations that would later be a vital resource for the astronomers of the European Renaissance. The great turning point, the Copernican revolution of the 16th century, was a moment when a single, radical idea that the Earth was not the center of the universe began to unravel the entire ancient worldview. This was a revolution that was not just about astronomy. It was a revolution in human thought, a profound and often unsettling decentering of humanity from a privileged place in the cosmos. The work of Johannes Kepler, with his discovery of the elliptical orbits of the planets, and of Galileo Galilei, with his groundbreaking telescopic observations, provided the crucial empirical evidence that would ultimately confirm the Copernican model and consign the ancient geocentric universe to the history books. The final piece of this classical clockwork universe was put in place by the towering figure of Sir Isaac Newton in the late 17th century. His law of universal gravitation was a stunning and powerful unification, a single mathematical principle that could explain both the fall of an apple and the orbit of the moon. It was a vision of a universe governed by precise, predictable, and universal laws, a vision that would define the scientific worldview for the next 200 years. The 19th century saw another great unification, that of electricity, magnetism, and light, in the beautiful and elegant equations of James Clerk Maxwell. This was the dawn of our understanding of the electromagnetic force, and it paved the way for the technological revolutions of the 20th century. But the 20th century would bring its own, even more profound, revolutions. Albert Einstein's theories of special and general relativity shattered the Newtonian concepts of absolute space and time, revealing a much more dynamic and interconnected reality, a four-dimensional space-time that is curved and warped by the presence of matter and energy. At the same time, the development of quantum mechanics was revealing the strange, probabilistic, and deeply counterintuitive nature of the subatomic world. And on the observational front, astronomers like Edwin Hubble were using the new, giant telescopes to discover that our Milky Way was just one of billions of other galaxies, and that these galaxies were all flying away from us, a sign that the universe itself was expanding. This led to the formulation of the Big Bang Theory, The idea that our entire vast cosmos began in an incredibly hot, dense, and singular state some 14 billion years ago. The launch of the first artificial satellite, Sputnik, in 1957 marked the beginning of a new era, the space age, an era where we could finally leave our home planet and begin to explore the cosmos directly. The journey to the moon, with the Apollo 11 mission in 1969, was a moment of profound, collective human achievement. A moment when we first set foot on another world and looked back at our own, fragile, pale blue dot, suspended in the vast, dark emptiness of space. This long and incredible journey of discovery, from the ziggurats of Babylon to the Sea of Tranquility, is a testament to the power of human curiosity, to our relentless and perhaps unique desire to understand our origins, our home, and our place in the grand and still unfolding cosmic story. Our entire vast and complex universe is governed by just four fundamental forces. They are the invisible threads that weave the fabric of reality, the cosmic rules of engagement that dictate how every single particle, from the smallest quark to the largest galaxy, interacts with every other. The first and most familiar of these is gravity. It is, by a huge margin, the weakest of the four forces, but it is also the one with an infinite range. It is a force that is always attractive, a gentle but relentless pull that every particle of matter and energy exerts on every other. It is the force that holds us to the Earth, that holds the Earth in its orbit around the Sun, that holds the Sun in its orbit around the center of the Milky Way, and that holds the billions of galaxies together in the vast, filamentary structures of the cosmic web. In the modern Einsteinian picture, gravity is not a force in the traditional sense, but is the very geometry of space-time, a curvature of the cosmic fabric caused by the presence of mass and energy. The second force is electromagnetism. It is a force that is vastly, unimaginably stronger than gravity. But it comes in two flavors, positive and negative charge, which means that on large scales, it tends to cancel itself out. It is the force that acts between charged particles, and it is responsible for almost all of the phenomena of our everyday lives. It is the force that holds atoms together, that binds molecules in chemical bonds, that gives rise to the structure and the properties of all the materials we see around us. It is the force behind electricity, behind magnetism, and behind light itself, which is a traveling wave of electromagnetic fields. It is a force that is described with exquisite precision by the theory of quantum electrodynamics, one of the most successful and well-tested theories in the entire history of science. The third and fourth forces operate only on the tiny subatomic scales of the atomic nucleus, and they are responsible for the very existence of the elements that make up our world. The strong nuclear force is, as its name suggests, the most powerful of all the forces. It is the superglue of the cosmos, the force that binds the quarks together to form protons and neutrons, and that binds the protons and neutrons together to form the atomic nucleus, overcoming the immense electromagnetic repulsion of the positively charged protons. It has an incredibly short range, operating only over distances smaller than the diameter of a proton. It is described by the theory of quantum chromodynamics. The weak nuclear force is the fourth and final force. It is weaker than both the strong force and electromagnetism, but still much stronger than gravity. It is also a short-range force, and it is responsible for certain types of radioactive decay, like beta decay, a process that is crucial for the nuclear reactions that power the sun. The weak force is the only one of the four that violates certain fundamental symmetries of nature. And this subtle asymmetry may be the key to understanding why our universe is made of matter and not antimatter. These four forces, in their beautiful and complex interplay, are responsible for all the richness and diversity of the universe we see. But the ultimate dream of physics is to find a deeper, underlying unity, a single, elegant theory that can describe all four of these seemingly disparate forces as different manifestations of a single, primordial superforce. We have already had some success in this quest for unification. In the 1970s, the electromagnetic and weak forces were unified into a single electroweak theory, a discovery that was a major triumph of the standard model of particle physics. The next great step would be to unify the electroweak force with the strong force, a step predicted by grand unified theories. And the final, ultimate goal, the holy grail of modern physics, would be to unify this grand unified force with gravity, to create a theory of everything. This is the challenge that theories like string theory are attempting to meet. The story of the four fundamental forces is the story of our ongoing quest to read the mind of God, to find the single, elegant, and beautiful set of principles that governs our entire, vast, and wonderful cosmos. The history of physics is, in many ways, a history of a series of profound and revolutionary discoveries that have revealed and then unified the fundamental forces of nature. The journey began in earnest in the 17th century with the work of Sir Isaac Newton. His law of universal gravitation was a moment of breathtaking unification. It revealed that the force that governs the fall of an apple on Earth is the very same force that governs the stately celestial dance of the planets and the moons. It was the first time that the terrestrial and the celestial realms had been brought together under a single mathematical law. For the next 2 centuries, the Newtonian universe, a clockwork cosmos of particles and forces moving in an absolute and separate space and time, reigned supreme. The next great unification came in the 19th century, with the work of a host of brilliant experimentalists and theorists, culminating in the magnificent synthesis of James Clerk Maxwell. He showed that the seemingly separate phenomena of electricity and magnetism were, in fact, two sides of the same coin, two aspects of a single underlying electromagnetic force. His beautiful and compact set of equations not only unified these two forces, but also revealed that light itself is an electromagnetic wave, a discovery that would pave the way for the invention of radio, of television, and of all of our modern but wireless technologies. The early 20th century brought two, even more profound, revolutions that would completely shatter the classical Newtonian worldview. Albert Einstein's special theory of relativity unified space and time into a single, four-dimensional continuum, space-time. And his general theory of relativity unified this space-time with gravity, revealing that gravity is not a force that propagates through space, but is the very curvature of space-time itself. His famous equation, E equals mc squared, revealed a deep and unexpected unity between mass and energy. At the same time, the development of quantum mechanics was revealing the strange, probabilistic, and deeply counterintuitive nature of the subatomic world. This new theory would provide the framework for understanding the two remaining and newly discovered fundamental forces. The strong nuclear force, the force that binds the atomic nucleus together, was first understood through the work of physicists like Hideki Yukawa in the 1930s, and was later given its complete, modern formulation in the theory of quantum chromodynamics. The weak nuclear force, responsible for radioactive decay, was first described by Enrico Fermi and was later incorporated into a unified theory with electromagnetism. This electroweak unification, developed in the 1960s and 70s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, was a monumental achievement, a triumph of the standard model of particle physics. It showed that at the high energies of the early universe, the electromagnetic and weak forces were indistinguishable. Two aspects of a single, underlying electro-weak force. This unification was confirmed with the discovery of the W and Z bosons, the massive force-carrying particles of the weak interaction, at CERN in the 1980s. The Standard Model is our current, and remarkably successful, theory of the electromagnetic, weak, and strong forces, and all the known elementary particles. It is a beautiful and predictive theory. But it is also an incomplete one. It does not include gravity, and it has a number of arbitrary to free parameters that we do not understand. The quest for a deeper unification continues. Grand unified theories attempt to unify the electro-weak and strong forces into a single, grand unified force. These theories predict that at even higher energies, the quarks and leptons would become indistinguishable, and that the proton, the stable building block of all ordinary matter, should eventually decay, albeit on a timescale that is far longer than the current age of the universe. The final, ultimate unification, the theory of everything, would bring gravity into this unified picture. This is the great, unfinished revolution in physics, the challenge that is being tackled by theories like string theory and loop quantum gravity. The history of our understanding of the fundamental forces is a story of a progressive unification, of a search for a deeper and simpler underlying reality. It is a story that has been written by some of the most brilliant and creative minds in the history of our species. A story that is a testament to the power of the human intellect to comprehend the deep and beautiful order of the cosmos. The development of quantum mechanics in the early 20th century was a revolution that not only changed our understanding of the subatomic world, but also provided a completely new language for describing the fundamental forces of nature. In the classical, pre-quantum picture, forces were described as fields, continuous entities that filled all of space. An electric charge, for example, creates an electric field, and another charge feels a force when it is placed in that field. But in the quantum picture, these fields are quantized. They are not continuous, but are made up of discrete, particle-like excitations, or quanta. A force is not a smooth push or pull. It is the result of the exchange of these force-carrying particles. This is the central idea of quantum field theory, the framework that underpins the entire Standard Model of particle physics. The electromagnetic force, in this picture, is mediated by the exchange of photons, the quantum particles of light. When two electrons repel each other, what is actually happening at a microscopic level is that they are constantly exchanging virtual photons. These photons are virtual because they exist for such a short time, as allowed by the Heisenberg uncertainty principle that they cannot be directly observed. But their collective effect is the very real and very familiar electromagnetic force. This beautiful and powerful theory, quantum electrodynamics, developed in the mid-20th century by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, is one of the most precisely tested theories in all of science. The same principle of particle exchange applies to the other forces. The strong nuclear force, which binds the quarks together to form protons and neutrons, is mediated by the exchange of particles called gluons. The theory of the strong force, quantum chromodynamics, is a much more complex and mathematically challenging theory than QED. But it is also a remarkably successful one, explaining why quarks are forever confined within protons and neutrons, and why the strong force becomes weaker at very high energies. The weak nuclear force is mediated by the exchange of two very massive force-carrying particles, the WW and Z bosons. The fact that these particles are so heavy is what makes the weak force so short-ranged. The discovery of the W and Z bosons at CERN in the 1980s was a stunning confirmation of the electro-weak theory, which unifies the weak and electromagnetic forces. In this unified picture, the photon and the W and Z bosons are all different manifestations of a single underlying electro-weak interaction. The great outstanding puzzle in this quantum picture of the forces is gravity. A quantum theory of gravity would require the existence of a force-carrying particle for the gravitational force, the graviton, but a consistent, mathematically sound theory of the graviton and its interactions has proven to be incredibly elusive. The attempt to apply the standard techniques of quantum field theory to gravity leads to uncontrollable, infinite answers that render the theory useless. This is the central challenge of quantum gravity. Theories like string theory and loop quantum gravity are our best attempts to solve this profound problem. The quantum mechanical picture of forces as the exchange of particles has completely revolutionized our understanding of the universe. It has revealed a hidden, subatomic world of incredible richness and complexity, a world governed by the strange and beautiful laws of probability and uncertainty. And it has provided a powerful and predictive framework for understanding three of the four fundamental forces of nature. The quest to complete this picture, to find a quantum description of gravity, and to unite it with the other forces, is the great unfinished adventure of modern physics. The story of our understanding of gravity is a story of two titans of science, Sir Isaac Newton and Albert Einstein. Newton, in the 17th century, gave us our first, comprehensive, mathematical theory of gravity. His law of universal gravitation, which states that every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them, was a work of breathtaking genius. It was a single, simple, and elegant law that could explain the fall of an apple, the orbit of the moon, the tides of the oceans, and the stately clockwork motion of the planets. It was a theory that unified the heavens and the earth, showing that they were governed by the same universal laws. Newton's theory of gravity and his three laws of motion would form the bedrock of physics for over 2 centuries. But for all its power and success, Newton's theory had a few subtle, conceptual problems. It described how gravity worked with exquisite precision, but it did not explain why. How did the sun know where the earth was? To exert a force on it, the idea of action at a distance, of a force that could be transmitted instantaneously across the empty vacuum of space, was something that Newton himself found to be deeply unsettling, and there were a few tiny observational discrepancies. The orbit of the planet Mercury, for example, was not behaving exactly as Newton's theory predicted. Its elliptical orbit was slowly precessing, or rotating, at a rate that could not be fully accounted for by the gravitational pull of the other planets. It was a tiny anomaly, a crack in the beautiful Newtonian edifice. And it was this crack that a young patent clerk named Albert Einstein would, in the early 20th century, blow wide open. Einstein's general theory of relativity, published in 1915, was a complete and radical rethinking of the nature of gravity, of space, and of time. In Einstein's picture, gravity is not a force that propagates through space. Gravity is the geometry of space. He proposed that space and time are not a static, passive background, but a dynamic, four-dimensional entity, space-time, that can be bent, curved, and warped by the presence of mass and energy. Massive objects, like the sun, create a deep dip or well in the fabric of space-time around them, and other objects, like the Earth, are not being pulled by a force. They are simply following the straightest possible path, a geodesic, through this curved space-time. It is like a bowling ball placed on a stretched rubber sheet, creating a depression, and a marble rolled nearby, which will then circle the bowling ball, not because it is being pulled by a force, but because it is following the curved contours of the sheet. This is a profound and beautiful idea, and it made a number of new and testable predictions. It correctly predicted the anomalous precession of the orbit of Mercury. It predicted that light itself should be bent by gravity, a prediction that was famously confirmed during a solar eclipse in 1919. And it predicted that time itself should be affected by gravity, that clocks in a stronger gravitational field should run slower than clocks in a weaker one, a phenomenon known as gravitational time dilation, which is a real and measurable effect that must be accounted for in the operation of our GPS satellite system. The discovery of gravitational waves in 2015 by the LIGO Observatory. The detection of the faint, propagating ripples in the fabric of space-time created by the collision of two black holes a billion light-years away was the final, stunning confirmation of Einstein's theory. It is a theory that has passed every experimental test with flying colors, and it remains our best and most complete description of the force that shapes the large-scale structure and the evolution of our entire cosmos. The development of theoretical frameworks is the very heart of the scientific enterprise. A theory is not just a collection of facts or a random guess. It is a coherent, logical, and mathematically consistent structure of ideas that can explain a wide range of observed phenomena and that can make new, testable predictions. In the study of the cosmos, we have two such grand, overarching frameworks: general relativity and quantum mechanics. General relativity, as we have seen, is our theory of the large-scale universe. It is a theory of gravity, of space-time, of the evolution of the cosmos as a whole. Its language is the language of differential geometry, of tensors, and of curved manifolds. Quantum mechanics, on the other hand, is our theory of the small-scale universe. It is a theory of particles, of fields, of the probabilistic and uncertain nature of the subatomic world. Its language is the language of wave functions, of operators, and of Hilbert spaces. These two frameworks are the twin pillars of modern physics, and they are both incredibly successful. But they are built on fundamentally different principles and seem to describe two mutually incompatible realities. The great unfinished quest of theoretical physics is to find a single, deeper framework that can unify these two. A theory of quantum gravity. And in this quest, a number of ambitious and highly speculative theoretical frameworks have been proposed. String theory is perhaps the most famous and well-developed of these. It is a framework that attempts to unify all the particles and forces of nature, including gravity, by positing that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different vibrational modes of these strings give rise to the different particles we observe. String theory is a framework of immense mathematical beauty and power, and it has the potential to solve some of the deepest puzzles in physics, from the nature of black holes to the origin of the universe. But it is also a theory that lives in a world of 10 or 11 space-time dimensions, and it has, so far, failed to make any unique, experimentally testable predictions. Loop quantum gravity is the leading alternative to string theory. It is a more conservative approach that does not try to unify all the forces, but instead focuses on the specific problem of quantizing Einstein's theory of general relativity. In this framework, space-time itself is not a smooth, continuous background, but is made of discrete, quantum atoms of space and time. These atoms are connected in a network called a spin network, and the evolution of this network creates a spin foam. Loop quantum gravity is a beautiful and conceptually radical idea, but it has struggled to show how the familiar smooth space-time of our macroscopic world can emerge from this underlying discrete quantum structure. Beyond these two main approaches, there are a host of other, more speculative, theoretical frameworks being explored. Causal dynamical triangulation is a computer-based approach that tries to build a quantum spacetime from simple, discrete building blocks. Twistor theory, an idea that goes back to Roger Penrose. attempts to describe reality not in terms of points in space-time, but in terms of more abstract, geometric objects called twistors. Asymptotic safety is a framework that suggests that a quantum theory of gravity might be well-behaved and predictive, even without the need for a full unification with the other forces. These theoretical frameworks are not just abstract, mathematical games. They are the tools that we use to explore the very limits of our understanding. They are the scaffolding upon which we build our picture of the universe. And while they are often highly speculative and far from being experimentally confirmed, they are essential to the progress of science. They are the source of new ideas, of new questions, and of new, unexpected connections. And it is from this vibrant and often chaotic ecosystem of competing theoretical frameworks that the next great revolution in our understanding of the cosmos will, one day, emerge. The idea that there might be more to the universe than the four familiar forces of nature is a tantalizing and recurring one in the history of physics. It is a possibility that is suggested by a number of deep, unresolved puzzles in our current understanding of the cosmos. Puzzles that seem to hint at the existence of a hidden, dark sector of reality, with its own particles and its own forces. String theory, our most ambitious framework for a unified theory, provides a natural and almost profligate home for new forces. In a world of 10 or 11 dimensions, the possibilities for new fields and new interactions are almost limitless. The specific nature of these forces would depend on the precise, and as yet unknown, geometry of the extra compactified dimensions. Some of these forces might be confined to the extra dimensions, while others could leak into our familiar three-dimensional world, their effects manifesting as a modification to gravity or as a new, incredibly weak interaction. The concept of extra dimensions itself, even outside the specific framework of string theory, provides a fertile ground for speculating about new forces. The Kaluza-Klein theory, first proposed in the 1920s, was a remarkable early attempt to unify gravity and electromagnetism by positing the existence of a single, tiny, circular extra dimension of space. In this theory, the electromagnetic force is not a separate, fundamental force, but is simply the manifestation of gravity in this hidden fifth dimension. While this specific model does not work in its simple form, the general idea that new forces can arise from the geometry of extra dimensions remains a powerful and recurring one in modern physics. The mystery of dark matter is another major motivation for the search for new forces. The standard cold dark matter model assumes that dark matter is a single, stable particle that interacts only through gravity and the weak nuclear force. This simple model has been remarkably successful in explaining the large-scale structure of the universe, but it has a number of small, but persistent, problems in explaining the detailed structure of individual galaxies. This has led to the idea that the dark sector may be more complex than we thought. Dark matter may not be a single particle, but a whole family of particles, with its own, new, dark forces that mediate interactions between them. A self-interacting dark matter model, for example, could help to explain why the cores of some galaxies are less dense than the simplest cold dark matter models predict. The mystery of dark energy is another potential signpost to new physics. While the simplest explanation for the accelerating expansion of the universe is a cosmological constant, this comes with the immense theoretical baggage of the vacuum catastrophe. This has led to the exploration of alternative, dynamical dark energy models, like quintessence, which propose that the acceleration is driven by a new, incredibly light scalar field, a field that would be associated with a new long-range fifth force. Even our understanding of gravity itself is not beyond question. Modified gravity theories, like Emond, propose that the law of gravity itself is different on galactic scales, which would explain the anomalous rotation of galaxies without the need for dark matter. While these theories face a number of significant challenges in explaining the full range of cosmological observations, They are a powerful reminder that our current understanding of gravity, as magnificent as it is, may not be the final word. The quest for a theory of quantum gravity is also a search for new forces. In most approaches to quantum gravity, at the incredibly high energies of the Planck scale, the familiar low-energy forces of nature are expected to be unified into a single primordial superforce. And the process by which this unified force breaks down into the four forces we see today as the universe cools and expands could leave behind a host of new, remnant forces and exotic particles. The search for new forces is a search at the very frontiers of our knowledge. It is a search that is guided by the subtle clues and the deep puzzles of our current theories. And it is a search that is being pursued with a host of new and powerful experimental and observational tools. It is a search that may, one day, reveal that the universe we see is just the tip of a much larger and much stranger cosmic iceberg. The framework of string theory, with its vision of a universe built from tiny, vibrating strings and extra hidden dimensions, is not just a potential theory of everything. It is also a powerful and prolific generator of new, speculative possibilities for the nature of reality, including the existence of new fundamental forces. In the world of string theory, the properties of the particles and forces we observe are not fundamental, but are a consequence of the geometry of the extra compactified dimensions. The way these extra dimensions are curled up, their shape, their size, their topology, determines the allowed vibrational modes of the strings, and therefore the entire particle zoo of our universe. Because string theory allows for a vast landscape of different possible geometries for these extra dimensions. It also allows for a vast landscape of different possible universes, each with its own unique set of physical laws and fundamental forces. In this context, the question is not, are there new forces, but why are the forces we see the only ones? The theory naturally predicts the existence of a host of other fields and forces beyond those of the standard model. Most of these new forces are expected to be either incredibly weak or to operate only over incredibly short distances, which is why we have not yet detected them. For example, the moduli fields that describe the shape and size of the extra dimensions would, if they exist, give rise to new, long-range, gravity-like forces. The fact that we have not observed any such forces puts very tight constraints on these models, but it is possible that these forces are so weak that they have, so far, escaped detection. Another possibility is that some of these new forces are confined to the extra dimensions, or that they only act on the particles of the dark sector, like dark matter. String theory also provides a natural framework for brane cosmology. The idea that our universe is a three-dimensional membrane floating in a higher dimensional bulk. In this scenario, there could be new forces that are mediated by particles that can travel in the bulk, not just on our brane. These bulk forces could have a different distance dependence than our familiar three-dimensional forces, and they could provide a new way for our universe to interact with other parallel brane worlds. The implications of new forces arising from string theory are profound. They could provide a natural explanation for the hierarchy problem, the question of why gravity is so incredibly weak compared to the other forces. In some brane world models, this is because gravity is the only force that is leaking into the large, extra dimensions, which dilutes its strength. New forces could also be the key to understanding the nature of dark matter and dark energy. Dark matter could be a particle that is charged under a new, dark force, but is neutral under our familiar electromagnetic force. Dark energy could be the result of a potential energy between our brane and another, or a manifestation of the complex geometry of the extra dimensions. The search for these new string theory-inspired forces is a major driver of research at the Large Hadron Collider and in a host of other high-precision tabletop experiments. At the LHC, physicists are looking for the direct production of new, heavy particles that could be the carriers of a new force, or for the production of Kaluza-Klein particles, which would be the signature of extra dimensions. The tabletop experiments are searching for tiny, subtle deviations from the known laws of physics, like a violation of the inverse square law of gravity at very short distances, or a new, incredibly weak, long-range force that could be detected by a sensitive torsion balance. So far, no definitive evidence for any of these new forces has been found, but the search continues. String theory, for all its mathematical elegance and its conceptual beauty, remains a purely theoretical framework. It is a magnificent and elaborate castle in the sky, a castle that is still waiting for a single, solid experimental foundation to be placed beneath it. The discovery of a new fundamental force, one that is predicted by, or at least consistent with, the framework of string theory, would be a monumental event. It would be the first tantalizing piece of experimental evidence that we are on the right track, that the strange and beautiful multidimensional world of string theory is not just a mathematical fantasy, but a true description of the deep, underlying reality of our cosmos. The quest for unification, the dream of a single, elegant theory that can explain all the forces and particles of nature, is one of the most powerful and enduring drivers of progress in fundamental physics. It is a quest that is based on a deep and almost aesthetic faith that the universe, at its most fundamental level, is simple, coherent, and beautiful. We have seen how this quest has led to a series of historic unifications, from Newton's unification of celestial and terrestrial gravity, to Maxwell's unification of electricity and magnetism, to the electroweak unification of the Standard Model. But the ultimate unification, the one that would bring the force of gravity into this quantum mechanical family, remains the great unfinished symphony of modern physics. Grand unified theories are the next logical step in this journey. They are a class of theories that attempt to unify the three forces of the Standard Model, the strong, the weak, and the electromagnetic forces, into a single, grand unified force. The central idea of QTs is that at incredibly high energies that existed in the very first moments after the Big Bang, these three forces were indistinguishable. They were all different aspects of a single, underlying interaction, governed by a larger and more symmetric mathematical group. As the universe cooled and expanded, this primordial symmetry was spontaneously broken, and the three forces froze out into the distinct and separate forces we observe today. Guts make a number of dramatic and testable predictions. They predict that the strengths of the three forces, which are very different at the low energies of our everyday world, should all become equal at the grand unification energy. And remarkably, when we extrapolate the measured strengths of the three forces to high energies, using the mathematics of the Standard Model, we find that they do not quite meet at a single point. But if we add the new particles predicted by supersymmetry into the calculation, they meet with stunning precision. This is one of the strongest, albeit indirect, pieces of evidence for both supersymmetry and grand unification. Another major prediction of most GUTs is that the proton, the seemingly stable building block of all ordinary matter, is not, in fact, stable. It should, very rarely, decay into lighter particles. This is because guts place the quarks and the leptons into the same unified family, and they predict the existence of new super-heavy particles that can mediate interactions that would turn a quark into a lepton, violating the conservation of baryon number and causing the proton to decay. The predicted lifetime of the proton in these theories is incredibly long, on the order of 10 to the power of 33 years or more, which is why we do not see the matter around us dissolving, but a number of large underground experiments, like the Super Kamiokande detector in Japan, are searching for these incredibly rare proton decay events. A definitive observation of proton decay would be a monumental discovery, a direct confirmation of grand unification. The ultimate unification, of course, would be a theory of everything, a theory that brings gravity into this unified picture. This is the challenge that is being tackled by string theory. In string theory, all the forces and particles of nature arise from the different vibrational modes of a single, fundamental entity, the string. It is, in this sense, the ultimate unified theory. And it is a theory that naturally includes gravity, as one of the vibrational modes of the string corresponds to the graviton. The implications of a successful unification theory would be profound. It would not just be the completion of our scientific picture of the world, it would also give us a new and powerful tool for understanding the very origin of the universe. It could explain the origin of the matter-antimatter asymmetry, the nature of cosmic inflation, and the reason why the universe has the specific properties it does. The quest for unification is a quest to read the first page of the cosmic story, to understand the single, simple, and beautiful seed from which all the complexity and diversity of our universe has grown. The quest for a theory of quantum gravity is the great outstanding challenge at the very frontier of modern theoretical physics. It is the quest to reconcile the two towering and seemingly incompatible pillars of 20th century science, Einstein's general theory of relativity and quantum mechanics. General relativity is our theory of the very large, a theory of gravity, of curved spacetime, of the evolution of the cosmos. Quantum mechanics is our theory of the very small, a theory of particles, of fields, of the probabilistic and uncertain nature of the subatomic world. And for most practical purposes, these two theories live in separate, non-overlapping domains. But in certain, extreme corners of the universe, in the infinitely dense singularity at the heart of a black hole, and in the fiery, unimaginably hot and dense crucible of the Big Bang, these two worlds collide. To understand these ultimate frontiers of reality, we need a single, coherent theory that can describe the quantum behavior of gravity itself. The fundamental conflict between the two theories lies in their different conceptions of space-time. In general relativity, space-time is a dynamic, physical entity, a smooth, continuous fabric whose geometry is determined by the distribution of matter and energy within it. In quantum mechanics, as it is currently formulated, space-time is a fixed, static, and absolute background, a passive stage upon which the probabilistic drama of quantum fields unfolds. A theory of quantum gravity must somehow resolve this fundamental tension. It must tell us how to describe a space-time that is both dynamic and quantum. Loop quantum gravity is one of the leading approaches to this profound challenge. It is a direct and, in some sense, conservative attempt to apply the principles of quantum mechanics to Einstein's theory of general relativity. In LQG, the smooth, continuous spacetime of general relativity is replaced by a discrete quantum structure. Space itself is not infinitely divisible, but is made of fundamental, indivisible atoms or quanta of space, each with a volume of about the Planck length cubed. These atoms are not located in space, they are space. They are connected together in a dynamic, evolving network called a spin network. The geometry of space, the very notions of distance and volume, are emergent properties of the combinatorial structure of this network. The evolution of this spin network in time creates a spin foam, a quantum history of space-time. Loop quantum gravity is a beautiful and conceptually radical theory. It makes a number of specific and dramatic predictions. It predicts that the singularity at the center of a black hole and the initial singularity of the Big Bang are resolved. In the world of LQG, there are no infinities. When a collapsing star reaches the Planck density, The quantum nature of space-time itself creates a powerful, repulsive force that prevents the formation of a true singularity, leading instead to a quantum bounce, the Big Bang. In this picture may not have been the beginning of time, but was simply a bounce from a previous, contracting phase of the universe. Loop quantum gravity has had a number of notable mathematical successes, but it also faces significant challenges. It has, so far, struggled to show how the familiar, smooth space-time of our low-energy world can emerge from its underlying discrete quantum structure. And it has not yet been able to incorporate the other forces and particles of the Standard Model into its framework. String theory takes a very different, and in many ways more ambitious, approach. Instead of trying to quantize gravity directly, it starts with the idea of unifying all the forces and particles of nature. As we have seen in string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And one of the vibrational modes of this string naturally corresponds to the graviton, the quantum particle of gravity. In this way, string theory is not just a theory of quantum gravity, it is a candidate theory of everything. But string theory, for all its mathematical elegance, comes with its own significant baggage, including the requirement of extra hidden dimensions of space and the vast landscape of possible solutions. The search for a theory of quantum gravity is a search that is pushing the limits of our scientific imagination. It is a search that is forcing us to question our most basic and deeply held intuitions about the nature of space, of time, of matter, and of reality itself. And it is a search that is, at present, severely hampered by a lack of experimental guidance. The effects of quantum gravity are only expected to become significant at the incredibly high energies and tiny distances of the Planck scale, a regime that is far beyond the reach of our current particle accelerators. And so, for now, the quest for quantum gravity remains a largely theoretical one, a beautiful and complex tapestry of mathematical ideas, a story that is still waiting for its first, crucial, experimental thread to be woven in. But the prize is a great one. A successful theory of quantum gravity would not just be the completion of the 20th century revolution in physics, it would be the beginning of a new one. It would be the key to unlocking the deepest secrets of the cosmos, the key to understanding the origin of the universe, the fate of a black hole, and the ultimate, quantum nature of the fabric of reality itself. In the strange and beautiful world of particle physics, the fundamental forces of nature are understood as the exchange of force-carrying particles, or bosons. But the particles that make up the matter of our universe, the fermions, like quarks and electrons, also play a crucial role in shaping the cosmos. The Standard Model of particle physics is our current, and remarkably successful, theory of all the known elementary particles and their interactions. It is a beautiful and predictive theory, a testament to the power of symmetry and mathematics to describe the fundamental workings of nature. The particles of the Standard Model are divided into two main families, the quarks and the leptons. The quarks are the building blocks of the protons and neutrons that make up the atomic nucleus. They come in 6 flavors: up, down, charm, strange, top, and bottom, and they are bound together by the strong nuclear force, which is mediated by the exchange of gluons. The leptons are a family of lighter particles that do not feel the strong force. The most famous lepton is the electron, the particle that orbits the atomic nucleus and is responsible for all of chemistry. The electron has 2 heavier cousins, the muon and the tau, and each of these 3 charged leptons has a corresponding neutral and incredibly elusive partner, the neutrino. These are the 12 fundamental matter particles of the Standard Model. They are organized into 3 generations of increasing mass, a pattern that is one of the deep, unexplained mysteries of the theory. The forces are mediated by the gauge bosons, the photon for the electromagnetic force, the W and Z bosons for the weak nuclear force, and the 8 gluons for the strong nuclear force. And the final piece of the Standard Model puzzle is the Higgs boson, a particle associated with the Higgs field, which pervades all of space. It is the interaction with this field that gives the fundamental particles their mass. The Standard Model is a triumph of 20th century physics. It has been tested with incredible precision in countless experiments at particle accelerators around the world. And it has, so far, passed every test with flying colors. But for all its success, we know that it is an incomplete theory. It does not include gravity. It does not explain the nature of dark matter or dark energy. It does not explain the matter-antimatter asymmetry of the universe. And it has a number of arbitrary, free parameters, the masses of the particles, the strengths of the forces that we must measure experimentally, but which the theory cannot explain. The search for physics beyond the Standard Model is one of the primary goals of modern particle physics, and there are a number of tantalizing, albeit inconclusive, hints that such new physics may be just around the corner. The mystery of the neutrino masses, for example, is a direct contradiction of the simple Standard Model, which predicts that neutrinos should be massless. The observation that neutrinos do, in fact, have a small but non-zero mass is the first definitive piece of experimental evidence for physics beyond the Standard Model. The existence of dark matter is another powerful clue. The Standard Model contains no particle that has the right properties to be the dark matter. This suggests that there must be a whole new dark sector of particles and forces that we have yet to discover. Supersymmetry is one of the most popular and well-motivated theoretical frameworks for physics beyond the Standard Model. It proposes a new fundamental symmetry between the two classes of particles, fermions and bosons, and it predicts that every known particle has a heavier superpartner. Supersymmetry can provide a natural candidate for the dark matter particle. It can help to solve some of the deep theoretical problems of the Standard Model, and it is an essential ingredient in most versions of string theory. The search for these superpartner particles is one of the main goals of the Large Hadron Collider. The relationship between the world of particle physics and the world of cosmology has become increasingly deep and intimate. The early universe was the ultimate particle accelerator, a place where the energies were so high that all the particles of the Standard Model, and perhaps many new undiscovered particles, were created in abundance. By studying the faint relic radiation from the Big Bang, the cosmic microwave background, cosmologists can place powerful constraints on the properties of these particles and on the physics of the early universe. The universe itself has become a giant, natural laboratory for particle physics. The quest to understand the fundamental particles and forces of nature is a quest that is being pursued on two fronts: the high-energy frontier of particle accelerators and the cosmological frontier of our observations of the universe. It is a quest that is driven by the hope that in the synergy between these two frontiers, in the dialogue between the very small and the very large, we will find the clues that will lead us to a new, deeper, and more complete understanding of the beautiful and still mysterious quantum universe we inhabit. Our understanding of the universe is not just built from abstract theoretical frameworks. It is grounded in the hard, cold, and often beautiful reality of observational evidence. Astronomy is, at its heart, an observational science. We cannot, for the most part, perform controlled experiments on the stars and the galaxies. We can only watch and listen and collect the faint, ancient light and other forms of radiation that travel to us across the vast, dark emptiness of space. And in the past century, our ability to do this has been revolutionized by a new generation of powerful, and often beautiful, tools of observation. The Hubble Space Telescope, launched in 1990, has become a cultural icon, a symbol of our species' insatiable curiosity, By placing a large 2.4-meter telescope above the blurring effects of the Earth's atmosphere, Hubble has given us a view of the cosmos that is of unprecedented sharpness and depth. It has provided us with stunning, iconic images of everything from the birth of stars in the pillars of the Eagle Nebula to the death of stars in the expanding shells of planetary nebula. It has allowed us to measure the expansion rate of the universe with unprecedented precision, to discover the existence of supermassive black holes at the centers of galaxies, and to take the first, tentative steps in analyzing the atmospheres of planets around other stars. The cosmic microwave background, the faint, relic afterglow of the Big Bang, is another of our most powerful observational probes. This faint, uniform glow of microwave radiation comes to us from all directions in the sky. And it is a snapshot of the universe when it was just 380,000 years old. A series of dedicated space missions, from COBE in the 1990s to WMAP and Planck in the 2000s, have mapped the tiny 1 part in 100,000 temperature fluctuations in the CMB with incredible precision. These fluctuations are the seeds of all cosmic structure, the primordial ripples from which all the galaxies and clusters of galaxies have grown. The detailed statistical properties of these fluctuations have provided a wealth of information about the age, the geometry, and the composition of our universe, and they have provided some of the strongest evidence for the theory of cosmic inflation and the existence of dark matter and dark energy. The discovery of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory has opened up a completely new and revolutionary window onto the universe. We can now not just see the cosmos, but we can also hear it. Gravitational waves are faint, propagating ripples in the fabric of space-time itself, created by the most violent and cataclysmic events in the universe. Like the merger of 2 black holes or 2 neutron stars, the ability to detect these waves is a stunning triumph of experimental physics, and it is allowing us to probe the nature of gravity and the properties of black holes in a completely new and unprecedented way. Planetary exploration through a fleet of robotic emissaries has transformed the planets and moons of our solar system from distant, abstract points of light into real, tangible worlds, each with its own unique geology, atmosphere, and history. The rovers on Mars, from Sojourner to Perseverance, have given us an on-the-ground view of the red planet, revealing a world that was once much warmer and wetter, a world that may have once been hospitable to life. The Cassini mission to Saturn gave us a decade of breathtaking images and data from the ringed planet and its incredible family of moons, including the discovery of a subsurface, liquid water ocean on the tiny, icy moon, Enceladus. The search for exoplanets, planets orbiting other stars, has been another of the great observational revolutions of the past few decades. Space missions like Kepler and TESS have used the transit method to discover thousands of new worlds, revealing that planets are incredibly common in our galaxy, and that many of them are small, rocky, and located in the habitable zone of their star, the region where liquid water could exist on their surface. The study of supernova, the explosive deaths of massive stars, has also provided a crucial piece of the cosmological puzzle. The observation that a particular type of supernova, a type Ia, always has the same intrinsic brightness has allowed astronomers to use them as standard candles to measure the vast distances to other galaxies. And it was the surprising dimness of these distant standard candles that led to the revolutionary discovery of the accelerating expansion of the universe and the existence of dark energy. This rich and diverse tapestry of observational evidence, from the photons of the CMB to the gravitational waves of colliding black holes, is the bedrock upon which our entire modern understanding of the cosmos is built. And it is a tapestry that is constantly growing, constantly being refined, constantly revealing new and unexpected patterns as we build new and more powerful tools to extend our senses and our understanding out into the vast, beautiful, and still mysterious universe. The astronomical phenomena we observe in the cosmos are not just beautiful and awe-inspiring spectacles, they are also powerful. Natural laboratories, places where the laws of physics are pushed to their absolute limits, and where the subtle signatures of new, undiscovered forces may be hiding in plain sight. The rotation of galaxies is a prime example. For decades, we have known that the outer stars of spiral galaxies are rotating much too fast. According to Newton's law of gravity, the rotation speed should decrease with distance from the galactic center, in the same way that the outer planets of our solar system orbit the Sun more slowly than the inner ones. But what we observe is that the rotation curves of galaxies are flat. The outer stars are moving just as fast as the inner ones. This discrepancy is one of the primary pieces of evidence for the existence of dark matter. A vast, invisible halo of matter that surrounds the visible galaxy and provides the extra gravitational pull needed to hold it together. But what if there is no dark matter? What if the anomalous rotation of galaxies is a sign that our understanding of gravity itself is incomplete? This is the idea behind modified gravity theories like MOND. These theories propose that on the very large scales of a galaxy, the law of gravity is different, that it becomes stronger at very low accelerations. This would explain the flat rotation curves without the need for any new exotic particles. The debate between dark matter and modified gravity is one of the major ongoing controversies in modern astrophysics. And it is a debate that is ultimately about whether the anomalies we see are a sign of a new substance or a new force. Gravitational waves, the faint ripples in space-time, are another powerful tool in the search for new physics. Einstein's general theory of relativity makes very precise predictions about the properties of the gravitational waves that should be emitted by events like the merger of two black holes, by comparing the detailed chirp signal detected by observatories like LIGO with the predictions of the theory. We can perform incredibly precise tests of general relativity in the strong field regime, where gravity is incredibly powerful. So far, Einstein's theory has passed every test with flying colors. But as the sensitivity of our detectors improves, we may begin to see subtle deviations from the predictions, deviations that could be the signature of a new long-range force, or the effect of extra hidden dimensions of space. The explosive deaths of massive stars, supernova, are another place where new forces could leave their mark. The core collapse of a massive star is an incredibly complex event, involving a delicate interplay between gravity, nuclear physics, and the physics of neutrinos. Our current computer simulations of supernovae still struggle to reliably reproduce the observed explosions. It is possible that this is simply because our models are not yet sophisticated enough to capture all the complex, three-dimensional hydrodynamics of the collapsing core. But it is also possible that there is a missing ingredient, a new particle or a new force that plays a crucial role in re-energizing the stalled shockwave and driving the explosion. The cosmic rays, the high-energy particles that constantly rain down on the Earth from space, are another potential messenger of new physics. Some of these particles have energies that are far beyond anything we can create in our terrestrial particle accelerators. The mechanisms that can accelerate particles to these ultra-high energies are still not fully understood, and they may involve new, exotic astrophysical objects or new, fundamental particle interactions. The detailed energy spectrum and composition of these cosmic rays could hold the key to unlocking these mysteries. The cosmic microwave background, the relic radiation from the Big Bang, is perhaps our most pristine and powerful probe of the fundamental laws of nature. The tiny temperature and polarization fluctuations in the CMB are a direct snapshot of the quantum fluctuations that were present in the very first moments of the universe's existence. The statistical properties of these fluctuations are incredibly sensitive to the physics of the early universe. Any new particles, any new forces, any deviation from the standard cosmological model that was present at that time would have left its subtle imprint on the patterns we see in the CMB today. By comparing our increasingly precise maps of the CMB with the predictions of different theoretical models, we can place powerful constraints on a wide range of new physics, from the properties of dark matter and dark energy to the nature of cosmic inflation. The universe is a vast and complex laboratory, and the astronomical phenomena we observe are the results of its ongoing experiments. And by carefully and patiently observing these phenomena, by looking for the subtle anomalies, the small discrepancies, the results that do not quite fit our expectations, we can hope to find the clues that will lead us to a new, deeper, and more complete understanding of the fundamental forces that shape our cosmic home. The intertwined mysteries of dark matter and dark energy, the two dominant and completely unknown components of our universe, are a profound and humbling testament to the vastness of our own ignorance. They are a sign that the beautiful and successful edifice of our current standard model of cosmology, for all its power and its predictive success, is built on a foundation that is 95% mysterious. Dark matter, the invisible scaffolding of the cosmos, makes up about 27% of the universe's mass energy content. We cannot see it, but we can feel its gravitational presence everywhere. It is the unseen hand that holds our galaxy together, that shapes the large-scale structure of the cosmic web, and that bends the light of distant galaxies in the cosmic funhouse mirrors of gravitational lensing. The leading hypothesis is that dark matter is a new, stable, and weakly interacting elementary particle, a WIMP, that was created in the hot, dense conditions of the early universe and has been gravitationally clumping ever since. But despite decades of searching, in deep underground detectors, in our most powerful particle accelerators, and in the signals from space, we have, so far, found no direct evidence for such a particle. This has led to a growing interest in alternative possibilities. Perhaps dark matter is not a WIMP, but a much lighter, wave-like particle called an action. Or perhaps it is not a single particle, but a whole dark sector of particles with its own new dark forces. This would mean that the universe we see, the universe of the standard model, is just one of two parallel and largely non-interacting worlds, a world of light and a world of darkness that are connected only through the gentle, universal touch of gravity. Dark energy is even more mysterious. It is the dominant component of the universe, making up about 68% of its total energy, and it is the source of the strange, repulsive force that is causing the expansion of the universe to accelerate. The simplest explanation for dark energy is that it is the cosmological constant, the intrinsic zero-point energy of the quantum vacuum itself. But as we have seen, this explanation comes with the immense theoretical baggage of the vacuum catastrophe, the 120 orders of magnitude discrepancy between the theoretical prediction and the observed value. This has led to a host of alternative and more exotic possibilities. Perhaps dark energy is not a constant, but a dynamic quintessence field, a field that is slowly evolving over cosmic time. Or perhaps it is a sign that our understanding of gravity itself is incomplete, that general relativity needs to be modified on cosmological scales. The connection between these two great dark mysteries is one of the most compelling and tantalizing questions in modern cosmology. Is it just a coincidence that the energy densities of dark matter and dark energy are of the same order of magnitude in the present epoch of the universe? This coincidence problem has led to the speculation that the two may be connected, that there may be a direct interaction or energy exchange between the dark matter and the dark energy fields. This would be a profound discovery, as it would imply the existence of a new, fifth fundamental force of nature, a force that operates primarily in the dark sector. The search for the nature of dark matter and dark energy is a search that is being pursued on all fronts, from the smallest scales to the largest. It is a search that is pushing the boundaries of our technology, of our theories, and of our very imagination. And it is a search that will, when it is finally successful, not just fill in the missing 95% of our cosmic inventory, but will likely trigger a new and profound revolution in our understanding of the fundamental laws of nature, of the origin and the ultimate fate of our universe, and of the deep, dark, and beautiful mystery that lies at the heart of our cosmic home. The cosmic rays, the constant invisible rain of high-energy particles that bombard the Earth from outer space, are a unique and powerful messenger from the most extreme and violent corners of the universe. They are the debris from cosmic cataclysms, the shrapnel from stellar explosions, the particles that have been accelerated to near light speed in the magnetic chaos of active galactic nuclei. And in the detailed properties of this cosmic radiation, in the subtle anomalies and the unexpected patterns, we may be seeing the first, faint hints of new, undiscovered forces of nature. One of the most significant and long-standing of these anomalies is the positron excess. The Alpha Magnetic Spectrometer, a sophisticated particle detector mounted on the International Space Station, has been meticulously measuring the composition of cosmic rays for over a decade. And it has confirmed, with unprecedented precision, a puzzling and unexpected feature at high energies. There are significantly more positrons, the antimatter counterparts of electrons, than our standard models of cosmic ray production and propagation can explain. Our standard picture is that most of the positrons in cosmic rays are secondary particles, produced when primary cosmic rays, like protons, collide with the atoms of the interstellar medium. But this process cannot account for the observed rising fraction of positrons at high energies. This suggests that there must be an additional primary source of high-energy positrons. One possibility is that this source is astrophysical. Nearby pulsars, the rapidly spinning, highly magnetized remnants of massive stars, are thought to be powerful particle accelerators, and they could be a significant source of high-energy electron-positron pairs. But another, more exciting, possibility is that the positron excess is a sign of new physics. In many models of dark matter, the dark matter particles can annihilate with each other, producing a shower of standard model particles, including electrons and positrons. A large concentration of dark matter, like the one at the center of our own galaxy, could be a powerful and previously unaccounted for source of high-energy positrons, a source that could explain the observed excess. A definitive detection of such a signal would be a monumental discovery, our first indirect glimpse of the dark matter particle and its interactions. Another intriguing puzzle is the origin of the ultra-high-energy cosmic rays, particles with energies that are millions of times greater than anything we can achieve in our most powerful terrestrial particle accelerators. The sources of these particles are a complete mystery. They are so energetic that they should be deflected very little by the magnetic fields of our galaxy, which means they should point back to their sources. But when we look in the directions from which they came, we see no obvious, powerful astrophysical accelerators. This has led to a host of speculative, top-down models for their origin. Perhaps they are not accelerated at all, but are the decay products of some new, super-heavy, and incredibly long-lived particle, a relic from the very early universe. Or perhaps they are the signature of a new, exotic astrophysical object, like a network of cosmic strings. Another anomaly lies in the behavior of muons, the heavy cousins of the electron. A number of experiments have reported a significant excess of muons in the particle showers that are created when high-energy cosmic rays hit the Earth's atmosphere. Our standard models of particle physics struggle to explain this muon excess. It may be a sign that our understanding of the strong nuclear force at these very high energies is incomplete. Or it may be a hint of new, undiscovered particles, or interactions that are being produced in these collisions. These cosmic ray anomalies are subtle, complex, and often contentious. They are at the very edge of our experimental capabilities, and it is always possible that they are the result of some subtle, instrumental effect or a misunderstanding of the complex astrophysical environments through which the cosmic rays travel. But they are also a powerful and important part of the scientific process. It is in these anomalies, in these places where the data does not quite fit our models, that the seeds of a new discovery are often sown. The cosmic rays are a free and incredibly powerful particle beam, a gift from the cosmos that allows us to probe the laws of nature at energies that are far beyond our terrestrial reach. And by patiently and carefully studying the messages they bring, we may one day find the first definitive clue that will lead us beyond the familiar territory of our current understanding and out into the new and undiscovered country of a deeper and more complete theory of the universe. The detection of gravitational waves in 2015 by the LIGO and Virgo collaborations was a moment of profound scientific and human achievement. It was the confirmation of a century-old prediction of Einstein's general theory of relativity, the culmination of a multi-decade and often frustrating experimental quest, and the opening of a completely new and revolutionary window onto the universe. For the first time, we could not just see the cosmos, but we could also hear the faint, propagating ripples in the fabric of space-time itself, and in the beautiful and incredibly informative chirp of these gravitational wave signals. We have a new and powerful tool in the search for new, fundamental forces. General relativity makes very precise and specific predictions about the properties of the gravitational waves that should be emitted by an event like the merger of two black holes. The theory predicts the exact shape of the waveform, the way its frequency and amplitude evolve as the two objects spiral into each other, merge, and then settle down into a single, final black hole. By comparing the observed signal with the predictions of the theory, we can perform incredibly precise tests of general relativity in the strong field regime, where gravity is incredibly powerful and space-time is highly curved. And so far, Einstein's theory has passed every test with flying colors. The observed waveforms match the predictions of general relativity with exquisite precision. But as the sensitivity of our detectors improves, and as we begin to collect a larger and more diverse sample of gravitational wave events, we may begin to see subtle deviations from these predictions, and these deviations could be the telltale signature of new physics. For example, some theories that propose a new fifth fundamental force predict that a binary system of two massive objects should lose energy not just to gravitational waves, but also to the radiation of this new force. This would cause the two objects to spiral into each other slightly faster than general relativity predicts, and it would leave a subtle, but potentially detectable, imprint on the early part of the gravitational wave signal. Other theories, like those with extra hidden dimensions of space, predict that gravitons, the quantum particles of gravity, could leak into these extra dimensions. This would cause the amplitude of the gravitational waves to decrease with distance in a way that is different from the standard inverse distance law of our familiar three-dimensional world. By comparing the observed strength of a gravitational wave signal with the estimated distance to its source, we can place powerful constraints on the existence of these extra dimensions. Gravitational waves can also be used to probe the nature of dark energy. The standard cosmological model assumes that dark energy is a cosmological constant, and that gravitational waves travel at the speed of light. But in some alternative, modified gravity theories, which attempt to explain the cosmic acceleration without dark energy, the speed of gravitational waves can be different from the speed of light. The observation in 2017 of both the gravitational waves and the electromagnetic light from the merger of two neutron stars, and the fact that these two signals arrived at Earth at almost exactly the same time after traveling for over 100 million light-years, has placed incredibly tight constraints on this class of modified gravity theories. A beautiful example of the power of multi-messenger astronomy. The ultimate goal of gravitational wave astronomy is to detect the stochastic background of gravitational waves from the very early universe. The faint primordial hiss of space-time itself, left over from the cataclysmic event of cosmic inflation. The detection of this background and the detailed measurement of its properties would be a discovery of monumental importance. It would be a direct confirmation of inflation, and it would give us a glimpse of the universe at energies that are 1 trillion times higher than those of the Large Hadron Collider. It would be a window into the physics of grand unification, of string theory, of the very birth of the fundamental forces of nature. The search for new forces with gravitational waves is still in its infancy. But it is a field of immense promise. The universe is a symphony of vibrations, of both electromagnetic and gravitational waves, and by learning to listen to both parts of this cosmic music, we are gaining a new, and much richer, and more complete picture of the deep and still mysterious laws that govern our cosmos. The cosmic microwave background, the faint relic afterglow of the Big Bang, is our most precious and informative fossil from the early universe. It is a snapshot of the cosmos when it was just 380,000 years old. A baby picture that has allowed us to determine the age, the geometry, and the composition of our universe with incredible precision. And in the subtle and seemingly random pattern of its temperature and polarization fluctuations, we have a powerful and versatile tool in the search for new fundamental forces and new physics beyond the standard model. The statistical properties of these fluctuations are a direct probe of the physics of the primordial universe. The standard model of cosmology, the lambda CDM model, which is based on the theory of cosmic inflation, makes very specific and precise predictions about what these statistics should look like. And so far, the observed CMB, as mapped by missions like WMAP and Planck, has been in stunningly good agreement with the predictions of this simple 6-parameter model. But as our measurements have become more and more precise, a few subtle and tantalizing anomalies have begun to emerge, hints that there may be more to the cosmic story than our standard model allows. For example, some studies have reported a slight, but statistically significant, lack of power in the temperature fluctuations on the very largest angular scales, a feature that is not easily explained by the simplest models of inflation. Others have pointed to a strange, and as yet unexplained, alignment of the largest features of the CMB with the geometry of our own solar system, the axis of evil, as it has been provocatively nicknamed. And there is the cold spot, a particularly large and cold region of the CMB that is statistically unlikely to be a simple, random fluctuation. These anomalies are still a matter of intense debate in the cosmological community. They may be nothing more than statistical flukes, the result of our human tendency to see patterns in random noise, or they may be a sign of some subtle, systematic error in our data or our analysis. But they may also be the first, faint whispers of new physics. The CMB is an incredibly sensitive probe of the number and the properties of the light, relativistic particles that were present in the early universe. The number of effective neutrino species, as it is known, can be precisely measured from the CMB data. The current measurement is in excellent agreement with the 3 known neutrino species of the standard model. But if there were a new light particle, a dark photon, or a sterile neutrino, that was present in the early universe, it would have left its subtle imprint on the CMB. An imprint that future, more precise, measurements could detect. The detailed polarization patterns of the CMB are another powerful window into new physics. The polarization of the CMB is created by the scattering of photons off of electrons in the primordial plasma. These polarization patterns come in two types: E modes, which are curl-free, and B modes, which have a swirling, vortex-like pattern. The standard model of cosmology predicts that there should be a certain level of E-mode polarization, and this has been observed with high precision. But it also predicts that there should be a much fainter, and as yet undetected, background of B-mode polarization, created by the primordial gravitational waves from cosmic inflation. The search for these primordial B-modes is one of the holy grails of modern cosmology. A definitive detection would be a smoking gun confirmation of inflation, and the strength of the signal would tell us about the energy scale at which inflation occurred, giving us a direct glimpse of the physics of grand unification. But B-modes could also be a sign of more exotic, new physics. Some theories that propose a new fundamental scalar or vector field in the early universe predict that this field could have generated its own unique pattern of B-mode polarization. And some theories that violate the fundamental symmetry of parity predict a correlation between the temperature and the B-mode polarization of the CMB, a signal that is strictly forbidden in the standard model. The CMB is a rich and complex tapestry of information, a cosmic Rosetta Stone that is allowing us to decipher the language of the early universe. And as we learn to read this ancient text with ever-increasing precision, with new and more powerful telescopes, both on the ground and in space, we may find that it contains not just the story of our known universe, but also the first, tantalizing clues of a new and even deeper chapter in the cosmic story. The quest to discover new, fundamental forces is not just a matter of passive observation. It is also a story of active, and often ingenious, experimental design. While the high-energy frontier of particle accelerators and the cosmological frontier of our observations of the universe are powerful and important avenues of research, there is a third, and increasingly vibrant, frontier in this search: the precision frontier of small-scale, high-precision, tabletop experiments. These experiments are not trying to create new particles by smashing things together at incredible energies. Instead, they are trying to detect the incredibly subtle and often fleeting effects of new forces by making measurements of familiar, low-energy systems with an unprecedented degree of precision. It is a search for the tiny, unexpected tremor in the fabric of reality that could be the sign of a new, hidden world. One of the classic, and still ongoing, examples of this approach is the search for a violation of the inverse square law of gravity at very short distances, Newton's law of gravity, and Einstein's general relativity. Both predict that the gravitational force between two objects should fall off precisely as the square of the distance between them. But many theories that propose new forces, particularly those with extra hidden dimensions, predict that at very short distances, typically on the scale of millimeters or less, there should be a deviation from this law. This is because, at these short distances, gravity would no longer be a purely three-dimensional force. It would begin to leak into the extra dimensions, changing its strength and its distance dependence. A number of incredibly sensitive experiments, using a device called a torsion balance, have been built to search for such a deviation. These experiments involve measuring the tiny, gravitational-like force between two carefully arranged test masses at sub-millimeter separations. So far, no deviation from the inverse square law has been found, which has placed very tight constraints on many of these theories. But the experiments are constantly being improved, pushing the limits of our knowledge ever deeper into the realm of the very small. Another related class of experiments is the search for a new long-range fifth force that is incredibly weak and that couples to matter in a way that is different from gravity. Some theories, for example, predict the existence of a new force that couples not to mass, but to baryon number or lepton number. Such a force would cause a tiny, composition-dependent violation of the weak equivalence principle. The cornerstone of general relativity, which states that all objects should fall with the same acceleration in a gravitational field, regardless of their composition. A number of highly sensitive multiverse experiments, which compare the acceleration of two test masses made of different materials in the gravitational field of the Earth or the Sun, have been built to search for such a violation. So far, the equivalence principle has held up with stunning precision, but the search continues. The quantum realm also provides a fertile ground for high-precision tests of fundamental physics. The anomalous magnetic moment of the electron and the muon, a tiny quantum correction to their magnetic properties, is one of the most precisely measured quantities in all of science. And it is also one of the most precisely calculated quantities in the Standard Model. The comparison between the experimental measurement and the theoretical prediction is a powerful test of the completeness of the Standard Model. Any discrepancy could be a sign of the virtual effects of new undiscovered particles or forces. And in fact, for the muon, there has been a long-standing and recently strengthened discrepancy of about 4 standard deviations between the experimental value and the theoretical prediction. This muon G2 anomaly is one of the most tantalizing hints of new physics that we currently have. These tabletop of precision experiments are the unsung heroes of the search for new forces. They may not have the glamour of a giant particle accelerator or a space telescope, but they are a crucial and complementary part of the scientific process. They are a testament to the power of human ingenuity to devise clever and sensitive ways to probe the deepest secrets of nature, not by brute force, but by the patient, meticulous, and beautiful art of precision measurement. And it may be in the tiny, almost imperceptible signal from one of these small, quiet experiments in a university basement somewhere that the first definitive evidence of a new fundamental force of nature will one day be found. The Large Hadron Collider at CERN is more than just the largest and most powerful particle accelerator ever built. It is a veritable discovery machine, a tool of unprecedented power in our quest to understand the fundamental constituents of matter and the forces that govern them. It is our most powerful microscope, allowing us to peer into the subatomic world with an energy and a resolution that is far beyond anything that was possible before. And in the fiery, miniature Big Bangs that are created when two protons collide at nearly the speed of light, we are searching for the telltale signatures of new, undiscovered forces of nature. The most direct way to search for a new force at the LHC is to look for the production of a new, heavy force-carrying particle. In the same way that the discovery of the W and Z bosons in the 1980s was a direct confirmation of the electroweak theory, the discovery of a new heavy Z' boson or a W' boson would be a smoking gun signature of a new fundamental force. These new particles would be unstable, decaying almost instantly into more familiar, standard model particles like electrons, muons, or jets of quarks. The signature of such a discovery would be a bump in the energy distribution of these decay products, a peak at a specific mass corresponding to the mass of the new particle. The ATLAS and CMS experiments at the LHC have been searching for such bumps across a wide range of possible masses and decay channels. So far, no definitive discovery has been made, which has placed very tight constraints on the existence of many of the simplest models of a new force. But the search continues, and with the ongoing high-luminosity upgrade of the LHC, the sensitivity of these searches will be dramatically increased in the coming years. Another, more indirect, way to search for new forces is to look for their effects on the behavior of the known, standard model particles. The existence of new forces, or of new heavy particles, can lead to subtle but measurable deviations from the predictions of the standard model in the rates of certain rare processes or in the detailed, angular distributions of the particles produced in a collision. These precision measurements are a powerful way to probe for new physics at energy scales that are even higher than the direct reach of the collider. The discovery of the Higgs boson at the LHC in 2012 was a monumental triumph for the Standard Model, the confirmation of its final missing piece. But the Higgs is not just the end of an old story. It may also be the beginning of a new one. The Higgs boson is a unique and mysterious particle, and it may be our most powerful portal to the physics that lies beyond the Standard Model. By precisely measuring the properties of the Higgs, its mass, its spin, its couplings to the other particles, we can search for any deviation from the predictions of the Standard Model. A small discrepancy could be a sign that the Higgs is not a simple elementary particle, but is a composite object, or that it is part of a larger, more complex Higgs sector with multiple Higgs bosons, as predicted by theories like supersymmetry. The Higgs could also be our window into the dark sector. If there is a new force that communicates between our world and the world of dark matter, the Higgs boson could be the portal through which this interaction takes place. This could lead to a new and previously invisible decay mode for the Higgs, where it decays into a pair of dark matter particles. The signature of such an event at the LHC would be missing energy, as the dark matter particles would fly out of the detector without leaving a trace. The search for these invisible Higgs decays is one of the most exciting and important parts of the LHC's ongoing research program. The Large Hadron Collider is a magnificent and complex machine, a testament to what humanity can achieve when it unites in the pursuit of fundamental knowledge. And while it has, so far, provided a stunning confirmation of our current Standard Model of particle physics, the story is far from over. The data it is collecting is a vast and largely unexplored territory, and within it, the clues that will lead us to the discovery of a new, fundamental force of nature may be patiently waiting, hidden in plain sight. The vast, dark, and empty spaces of the cosmos are not the only places where we can search for the subtle signatures of new fundamental forces. Our own galactic backyard. The increasingly crowded and complex environment of near-Earth space is also a laboratory for fundamental physics, and the growing fleet of satellites that we have placed in orbit around our planet are not just tools for communication, for navigation, and for observing the Earth. They are also incredibly sensitive, and often unwitting, detectors of the deep, underlying laws of nature. Satellite experiments have played a crucial role in testing the foundations of our understanding of gravity. The LaGOS satellites, for example, are simple, passive, and incredibly dense spheres covered with corner-cube retroreflectors. By bouncing laser beams off of these satellites from ground stations and precisely measuring the round-trip travel time, we can track their orbits with millimeter-scale precision. This has allowed for incredibly precise tests of general relativity, including the measurement of frame dragging, the subtle twisting of space-time around a rotating body like the Earth. Any deviation from the predictions of general relativity in these precise orbital measurements could be a sign of a new, long-range fifth force. The Gravity Probe B mission was another, beautiful, and incredibly challenging satellite experiment designed to test two of the key predictions of general relativity. It used 4 ultra-precise and cryogenically cooled gyroscopes to measure the curvature of space-time around the Earth and the frame-dragging effect. The results were in perfect agreement with Einstein's theory, providing another powerful confirmation of its validity. Satellites are also powerful tools in the search for dark matter. The Alpha Magnetic Spectrometer on the International Space Station, as we have seen, is making incredibly precise measurements of the composition of cosmic rays. A definitive detection of an excess of antimatter particles, like positrons or antiprotons, that could be unambiguously attributed to the annihilation of dark matter particles in our galactic halo, would be a revolutionary discovery. Other satellite missions, like the Fermi Gamma Ray Space Telescope, are searching for the gamma rays that should be produced in these dark matter annihilation events. By searching for a faint, diffuse glow of gamma rays from the center of our galaxy, or from nearby dwarf galaxies that are thought to be rich in dark matter. These experiments are placing powerful constraints on the properties of the dark matter particle. The cosmic microwave background, our most powerful cosmological probe, has also been mapped with exquisite precision by a series of dedicated satellite missions from COBE to WMAP and Planck. These satellites have given us a baby picture of our universe, and in the detailed statistical properties of this picture, we can search for the subtle imprints of new physics. A future, dedicated CMB polarization satellite, like the proposed Lightbird mission, would be a powerful tool in the search for the primordial gravitational waves from cosmic inflation. A discovery that would give us a direct glimpse of the universe at the incredible energies of grand unification, the very energies where new forces of nature are expected to emerge. The near-Earth space environment is a unique and valuable laboratory. It is a place where we can perform controlled, high-precision experiments on a scale that is impossible on the ground. And as our technology for building and for operating satellites becomes more and more sophisticated, we will be able to use this laboratory to probe the fundamental laws of nature with an ever-increasing precision, searching for the tiny, subtle clues that will lead us to a new and deeper understanding of the forces that shape our cosmos. The quest to discover new fundamental forces is a quest that is being pursued on all fronts, from the high-energy collisions of particle accelerators to the high-precision measurements of tabletop experiments, to the vast cosmic scales of our astronomical and cosmological observations, and to decipher the subtle clues that are emerging from all of these different frontiers. We need a new and more powerful set of theoretical tools. The development of these tools is one of the most vibrant and exciting areas of modern theoretical physics. At the heart of this effort is the ongoing quest to move beyond the standard model of particle physics. The standard model, for all its success, is an incomplete theory. It is a beautiful and predictive description of the known particles and forces, but it leaves many of the deepest questions of fundamental physics unanswered. And so, a whole ecosystem of theoretical frameworks has been developed to try and address these questions and to provide a structure for our search for new forces. Supersymmetry, as we have seen, is one of the most well-motivated and deeply studied of these frameworks. It provides a natural candidate for the dark matter particle. It helps to solve some of the deep theoretical problems of the standard model. And it is an essential ingredient in most versions of string theory. And it predicts a host of new particles and new interactions that we can search for at the LHC. Theories with extra dimensions are another, powerful and recurring. Theme. These theories, from the simple Kaluza-Klein idea to the complex multidimensional world of string theory, provide a natural and geometric origin for new forces. The search for the signatures of extra dimensions, either through the production of Kaluza-Klein particles at the LHC or through the search for a deviation from the inverse square law of gravity at short distances, is a major focus of experimental physics. Grand unified theories are another important class of theoretical models. They provide a beautiful and compelling framework for unifying the strong, weak, and electromagnetic forces. And they make the dramatic prediction of proton decay, a prediction that is being tested in large, underground detectors. The theoretical implications of a discovery of a new force would be profound. It would not just be about adding a new particle or a new term to our equations. It would be a moment of deep conceptual realignment. It would force us to rethink our most basic assumptions about the structure of the universe, about the nature of symmetry, about the origin of the forces we see. It would be a clue, a signpost, a breadcrumb that would lead us down a new and previously unknown path towards a deeper and more complete understanding of the cosmos. The process of theoretical physics is a constant, and often beautiful, dialogue between mathematics and observation. The theorists, guided by principles of symmetry, of elegance, and of mathematical consistency, propose new ideas, new frameworks, new possibilities. And the experimentalists, with their ingenious and ever more powerful tools, go out and test these ideas against the hard, cold reality of the physical world. It is in this dynamic, creative, and often messy interplay between theory and experiment that scientific progress is made. And as we stand on the threshold of a new era of discovery, with a new generation of powerful experiments and observatories coming online, the prospects for a breakthrough, for the discovery of a new, fundamental force that will forever change our picture of the universe, have never been brighter. The universe is a deep and still largely unwritten book, and we are, for the first time in our history, beginning to learn how to decipher its most fundamental and beautiful language. The discovery of a new, fundamental force of nature would not just be a revolution in physics, it would be a revolution in our entire human worldview. It would be a moment of profound, and perhaps unsettling, reorientation, a moment when our map of reality is suddenly and irrevocably redrawn. The four forces we currently know, gravity, electromagnetism, and the two nuclear forces are the pillars of our scientific understanding of the world. They are the basis for our technology, our chemistry, our biology, our cosmology. They are the rules of the game. A fifth force would not just be a new rule, it would be a sign that the game itself is far larger and far stranger than we had imagined. The immediate impact would be on the field of particle physics. The standard model, our beautiful and successful, but ultimately incomplete, theory of the fundamental particles and forces would be superseded. The discovery of a new force would provide the crucial experimental clue that would guide us towards a more complete and more fundamental theory, whether that be supersymmetry, or a theory with extra dimensions, or something else entirely that we have not yet even dreamed of. It would be the beginning of a new standard model. The impact on cosmology would be equally profound. A new force could be the key to unlocking the twin mysteries of dark matter and dark energy. If the new force is a dark force that communicates between the particles of the dark sector, it would open up a whole new realm of dark chemistry and dark physics. If the new force is a long-range, gravity-like force, it could explain the accelerating expansion of the universe without the need for a cosmological constant. A new force could also have played a crucial role in the very first moments of the universe's existence, in the process of cosmic inflation, or in the origin of the matter-antimatter asymmetry. The discovery of a new force would give us a new tool, a new lens, through which to view our cosmic history. But the implications would not just be theoretical. A new force could, in the long run, have profound practical applications. The history of physics is a history of fundamental discoveries leading to transformative technologies. The discovery of electromagnetism gave us electricity, radio, and computers. The discovery of the nuclear forces gave us nuclear power and nuclear medicine. What new technologies might a new force enable if the force could be harnessed? Could it lead to new forms of energy, of propulsion, of communication? These are speculative questions, but they are the kind of questions that a fundamental discovery inevitably raises. And the philosophical implications would be perhaps the most profound of all. A new force would be a stark and powerful reminder of the provisional nature of our own knowledge. It would be a lesson in intellectual humility, a reminder that the reality we perceive with our senses and the reality we describe with our current theories is not the whole of reality. It would be a sign that the universe is, and perhaps always will be, more mysterious, more complex, and more wonderful than our current understanding. It would challenge our sense of our own place in the cosmos. The discovery of a new force would be a moment of deep, human connection to the universe. It would be a moment when we, as a species, have listened carefully enough to the cosmos to hear a new and previously unheard note in its grand and ongoing symphony. It would be a moment of awe, of wonder, and of a renewed sense of our own privileged and beautiful place as the part of the universe that is, for now, doing the listening. The existence of new forces would not just add a new chapter to our physics textbooks. It could fundamentally reshape the very structure and the evolution of the cosmos, creating a universe that is far richer, more dynamic, and more complex than the one described by our current four-force model. Imagine, for example, a new long-range force that is repulsive for matter and attractive for antimatter. Such a force, if it existed, could have had a profound impact on the early universe. It could have led to a large-scale separation of matter and antimatter, creating vast domains of the universe that are dominated by one or the other. Our observable universe, with its overwhelming dominance of matter, might just be one, small, matter-dominated domain in a much larger cosmos that is, on average, symmetric. This would be an elegant solution to the matter-antimatter asymmetry problem. Or imagine a new force that couples to dark matter. This dark force could cause the dark matter particles to self-annihilate or to decay, producing a faint, diffuse glow of gamma rays or other standard model particles that we could detect with our telescopes. Or it could be a repulsive force, preventing the dark matter from clumping together too densely in the centers of galaxies, which could explain some of the observed discrepancies with the simplest cold dark matter models. The existence of a dark force would mean that the dark sector of the universe is not just a simple, inert, and gravitationally acting substance, but is a rich and complex world of its own, with its own dark chemistry and its own dark atoms. New forces could also have a profound impact on the life cycle of stars. The process of nuclear fusion in the core of a star is a delicate balance between the inward pull of gravity and the outward push of the thermal pressure from the fusion reactions. A new force, if it could operate within the extreme conditions of a stellar core, could alter this balance. It could change the rate of fusion, leading to stars with different luminosities, different temperatures, and different lifespans. It could also influence the final, explosive death of a massive star in a supernova. The complex physics of a core collapse supernova is still not fully understood, and it is possible that a new short-range force plays a crucial role in re-energizing the stalled shockwave and driving the explosion. The fundamental constants of nature themselves might not be so constant in a universe with new forces. Many theories that propose new ultralight scalar fields predict that these fields could couple to the particles of the standard model, and as the value of the field evolves over cosmic time, it could cause the constants of nature, like the fine structure constant or the ratio of the proton to electron mass, to slowly change. The search for a temporal or spatial variation in these constants is a major focus of high-precision observational astronomy. A definitive detection of such a variation would be a revolutionary discovery, a sign that the laws of physics are not a fixed, static set of rules, but are part of the dynamic, evolving fabric of the cosmos itself. Finally, new forces could lead to the existence of entirely new, exotic, and stable macroscopic objects, in the same way that the strong nuclear force allows for the existence of atomic nuclei. A new confining dark force could allow for the existence of dark nuclei or dark atoms. And on a much larger scale, some theories predict the existence of cueballs or solitons, stable, lump-like configurations of a new scalar field. That could be a form of dark matter or could have other observable astrophysical consequences. The universe is a vast and creative laboratory, and it is entirely possible that the four forces we know are just the tip of a much larger and much stranger cosmic iceberg. The search for new forces is a search for a more complete and more accurate picture of this hidden reality. The discovery of a new fundamental force would not just be a matter of adding a new column to the table of known interactions in our physics textbooks. It would be a moment of deep conceptual upheaval, a moment that would force us to fundamentally reevaluate and likely to revise our most successful and cherished theory of the subatomic world, the Standard Model of particle physics. The Standard Model is a beautiful and remarkably predictive theory, but it is also a strangely ad hoc and incomplete one. It is a house that is beautifully decorated and structurally sound, but whose architectural plans are a mystery. The discovery of a new force would be like finding a hidden blueprint, a clue that would reveal the deeper underlying principles upon which the house was built. For example, a new force could be the key to solving the hierarchy problem. The question of why the Higgs boson is so incredibly light compared to the natural Planck scale of gravity. The existence of a new force and its associated new particles at the TeV energy scale could provide a natural explanation for this lightness. Through mechanisms like supersymmetry or extra dimensions, a new force could also be the key to understanding the pattern of the particle masses themselves. The Standard Model has a strange three-generation structure for the quarks and the leptons, with each generation being a heavier, but otherwise identical copy of the one before it. The masses of these particles span a huge range and seem to follow no discernible pattern. They are free parameters that we must simply measure and plug into the theory. A new flavor force that communicates between the different generations could be the key to explaining this mysterious family structure and the origin of the particle masses. A new force could also be the missing piece in the puzzle of grand unification. As we have seen, the strengths of the three forces of the Standard Model seem to almost, but not quite, meet at a single point at very high energies. The existence of new particles associated with a new force or with a framework like supersymmetry could change the way these force strengths evolve with energy, causing them to meet with perfect precision at a single grand unification point. This would be a powerful and beautiful sign that we are on the right track towards a deeper, unified understanding of nature. The discovery of a new force would also, almost certainly, come with the discovery of a new force-carrying boson. And the properties of this new particle, its mass, its spin, its couplings to the other particles would provide a wealth of information about the nature of the new interaction and the underlying symmetry group from which it arises. It would be a new window into the mathematical structure of the universe. The Standard Model is a theory that is, in many ways, a victim of its own success. It works so well that it has, for decades, provided very few clues about where to look for the new physics that we know must lie beyond it. The discovery of a new force would be the first definitive crack in this beautiful but ultimately incomplete edifice. It would be the thread that we could begin to pull on, a thread that could lead us to unravel the deeper and more profound tapestry of a true, unified theory of everything. The laws of thermodynamics, the great overarching principles that govern the flow of energy and the evolution of disorder in our universe, are so robust and so universally applicable that they are often considered to be the most fundamental laws of all. But even these seemingly unassailable laws could be challenged, or at least profoundly recontextualized, by the discovery of a new fundamental force. The first law of thermodynamics, the conservation of energy, states that the total energy of an isolated system is always constant. But what if our universe is not a truly isolated system? Many theories that propose new forces, particularly those with extra dimensions, envision our universe as a brain floating in a higher dimensional bulk. In this scenario, it is possible that energy could leak from our brain into the bulk, or from the bulk onto our brain. This would manifest in our universe as an apparent violation of energy conservation. A high-energy particle collision at the LHC, for example, could create a graviton that escapes into the extra dimensions, carrying energy with it. The signature of such an event would be missing energy in our detectors. The search for such missing energy events is a major focus of the LHC's research program, and a definitive observation would be a stunning confirmation of the existence of extra dimensions and a sign that the law of energy conservation only holds for the total higher dimensional system. The second law of thermodynamics, the law of increasing entropy, is what gives time its arrow. It is the law that says that the universe as a whole is moving towards a state of greater disorder, of heat death. But a new force could have a profound impact on this cosmic story. For example, some speculative models of dark energy propose that it is not a constant, but a dynamic field that is slowly decaying, releasing energy into the universe. This would be a constant source of negentropy, of new order, that could counteract the overall trend of increasing entropy. In a more radical scenario, a new force could be linked to the very origin of the low-entropy initial conditions of the universe. Perhaps the process that gave rise to the Big Bang, whether it was the decay of a false vacuum in an inflationary model or the collision of two branes in a cyclic one, was a process that was governed by a new entropy-reducing force, a force that reset the cosmic clock and created the highly ordered state from which our universe's arrow of time could begin. The connection between gravity and thermodynamics is another deep and mysterious area where a new force could play a role. The discovery that black holes have a temperature and an entropy. A discovery that was born from the work of Jacob Bekenstein and Stephen Hawking is one of the most profound insights in all of theoretical physics. It suggests a deep and as yet not fully understood connection between the geometry of space-time, the laws of quantum mechanics, and the principles of thermodynamics. A new force could modify the properties of black holes, changing their entropy, their temperature, and their rate of evaporation. This would have a profound impact on our understanding of this deep holographic connection between gravity and information. The laws of thermodynamics are not just abstract, physical principles. They are the very framework that makes life and complexity possible. We are creatures of entropy, beings who maintain our own local state of high order by consuming energy and exporting disorder into our environment. The existence of a strong arrow of time, of a universe that is far from thermal equilibrium, is the ultimate precondition for our own existence. The discovery of a new force, one that could change the cosmic story of energy and entropy, would therefore be a discovery that would not just change our physics. It would change our understanding of our own deep and intimate connection to the thermodynamic unfolding of the cosmos. The discovery of a new fundamental force would not just be a revolution in science, it would be a revolution in philosophy. It would be a moment that would force us to confront, in a new and powerful way, our most basic and deeply held assumptions about the nature of reality, of knowledge, and of our own place in the cosmos. At its most fundamental level, it would be a profound lesson in epistemological humility. It would be a stark and undeniable reminder that our current scientific picture of the world, as successful and as powerful as it is not a final and complete description of reality. It is a provisional map, a work in progress, a single frame in a long and still unfolding movie of discovery. The existence of a force that has been operating in the universe for 14 billion years, a force that has been shaping the evolution of the cosmos and the very fabric of reality, and yet has remained completely hidden from us until now, should fill us with a deep sense of wonder and a deep sense of caution about the hubris of our own knowledge. A new force would also reignite the age-old philosophical debate about the nature of scientific truth. Does science progress in a linear, cumulative way, with each new discovery adding another? solid brick to the edifice of our knowledge, or does it progress through a series of paradigm shifts? As the philosopher of science Thomas Kuhn argued, where our entire worldview, our entire way of seeing and of understanding the world is periodically and radically overturned. The discovery of a new fundamental force would be a paradigm shift of the highest order. It would force us to not just add a new chapter to our textbooks, but to rewrite the entire book from the beginning. The implications for our understanding of causality could also be profound. Our classical, intuitive notion of causality is a local and linear one. Things are influenced by their immediate surroundings, and cause always precedes effect. But the quantum world, with its phenomena of entanglement and non-locality, has already challenged this simple picture. A new force, particularly one that is associated with extra dimensions or with a deeper quantum gravitational reality, could have even stranger causal properties. It could be a force that connects distant parts of the universe in a way that is not limited by the speed of light, or a force that is linked to the probabilistic and nonlinear nature of time itself. This would force us to adopt a much more holistic, more interconnected, and less mechanistic view of the universe. The discovery of a new force would also have a deep impact on the great existential questions that have always been at the heart of the human quest for meaning. It would, in a sense, make the universe a larger and more mysterious place. It would open up new possibilities for the nature of reality, for the existence of other worlds, of other dimensions, of other hidden aspects of the cosmos. This can be a source of both exhilaration and of a kind of cosmic vertigo. But it is a vertigo that is, in the end, a healthy one. It is the feeling that comes from standing at the edge of a great and newly discovered frontier. It is the feeling of a mind that is expanding to accommodate a larger and more wondrous reality. And finally, the discovery of a new force would have a profound impact on the dialogue between science and spirituality. It would be a powerful reminder that the universe is not a closed, fully understood, and disenchanted machine, but is an open, evolving, and deeply mysterious reality. It would be a discovery that could foster a renewed sense of awe, of reverence, and of a shared human participation in the ongoing, and perhaps infinite unfolding of a cosmic mystery. The sheer scale of the universe, the vastness of the distances, and the immensity of the timescales is a concept that is almost impossible for the human mind to truly, intuitively grasp. Our brains evolved to navigate the mesoscopic world of our immediate terrestrial environment, a world of meters and of years. The language of cosmology is a language of numbers so large that they lose all their familiar meaning. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. A light-year, the distance that light travels in a single year, is about 6 trillion miles. This is a distance that is already far beyond our direct human experience. But the universe contains structures that are built on scales that are even more mind-boggling. Our own Milky Way galaxy, our home, is a swirling, spiral city of about 200 billion stars, and it is about 100,000 light-years across. To travel from one side of our galaxy to the other, even at the speed of light, would take 100,000 years. And our galaxy is not alone. It is part of a small, gravitationally bound cluster of about 50 galaxies called the local group. The local group, in turn, is just one small, outlying component of a much larger structure. The Virgo supercluster, a vast collection of thousands of galaxies that stretches across about 110 million light-years of space. And even this immense supercluster is just a single filament in an even grander cosmic structure, On the very largest scales, the universe is organized into a cosmic web, a vast, intricate, and beautiful network of galaxy clusters and superclusters, arranged in long, thin filaments and broad, flat walls, all surrounding immense, nearly empty cosmic voids. The Laniakea supercluster, the galactic superstructure that our own Milky Way calls home, is a sprawling, filamentary metropolis of about 100,000 galaxies, and it is over 520 million light-years in diameter. And as we have seen, there are even larger structures, like the recently discovered Hercules Corona Borealis Great Wall, a concentration of galaxies that seems to stretch for a staggering 10 billion light-years, a structure so large that it challenges our most basic cosmological principle of homogeneity. The history of the universe is a story that is played out on an equally unimaginable timescale. The universe is about 13.8 billion years old. If we were to compress this entire cosmic history into a single calendar year, with the Big Bang happening at the first second of January 1st, then our own Milky Way galaxy would form sometime in May. Our solar system would not appear until early September. The first, simple, single-celled life on Earth would emerge by the end of September. The great age of the dinosaurs would be a brief period in the last week of December, and the entire recorded history of human civilization, from the first cities to the present day, would take up just the last 10 seconds of New Year's Eve. Our own individual human lifespan, in this cosmic calendar, is less than the blink of an eye. This vastness of space and time is not just a source of intellectual wonder, it is a profound, and perhaps necessary, source of existential perspective. It is a powerful antidote to our own human-centered arrogance. It is a reminder that our own lives, our own problems, our own conflicts are, in the grand scheme of things, incredibly small and fleeting, but it is also a source of deep and perhaps paradoxical meaning. The fact that in this vast and largely empty cosmos, on a small, insignificant planet orbiting a very average star, a form of matter has arisen that is capable of looking back at the universe, of understanding its scale, of deciphering its laws, of appreciating its beauty, is perhaps the most wonderful and astonishing fact of all. We are the universe's way of knowing itself. We are the part of the cosmos that has woken up. And our tiny, fleeting, and precious moment of conscious existence is imbued with a significance that is, in its own way, as vast as the cosmos itself. The existence of new fundamental forces would not just add a new layer of complexity to our understanding of the universe. It could fundamentally reshape the very process of cosmic structure formation, leading to a universe with a different architecture, a different history, and a different ultimate fate. The story of structure formation in our standard four-force model is a relatively simple and elegant one. It is a story that is governed primarily by the gentle, patient, and relentless pull of gravity. In the early universe, there were tiny quantum fluctuations in the density of matter. The regions that were slightly denser than average had a slightly stronger gravitational pull, and they began to attract the matter from the surrounding, less dense regions. This is a process of gravitational instability, a classic rich-get-richer scheme. Over billions of years, this process has amplified the initial tiny density fluctuations into the vast cosmic web of galaxies, clusters, and superclusters that we see today. The invisible dark matter plays a crucial role in this story, because dark matter does not interact with light. It was able to start clumping together much earlier than the normal. Baryonic matter, forming the deep gravitational wells or halos into which the normal matter would later fall, eventually cooling and condensing to form the stars and the galaxies. But what if there was another force at play in this cosmic drama? A new long-range force could have a profound impact on this process. A new attractive force, for example, could have accelerated the process of structure formation, leading to the formation of galaxies and clusters much earlier in cosmic history. This could be a potential solution to the puzzle presented by the James Webb Space Telescope, which seems to be finding galaxies that are surprisingly mature and well-formed at very early times. A new repulsive force, on the other hand, could have hindered the process of gravitational collapse, leading to a universe with a less clumpy, more diffuse structure. This could help to solve some of the small-scale challenges of the standard cold dark matter model, like the core cusp problem. The fact that the centers of some galaxies seem to be less dense than our simplest models predict. A new force that only acts on dark matter, or ISO, would be particularly intriguing. It could cause the dark matter to behave in a much more complex way, allowing it to cool down, to dissipate energy, and to form its own dark structures, like dark matter disks or even dark atoms. The universe could be home to a whole, hidden, and parallel world of dark matter structures, a world that we can only perceive through its subtle, gravitational influence. The evolution of the cosmic voids, the vast, empty regions of the cosmic web, would also be affected by a new force. A repulsive force, like dark energy, is what drives the growth of these voids, pushing the matter out of them and into the surrounding filaments and walls. A new force could change the dynamics of this process, leading to voids with different sizes, different shapes, and a different degree of emptiness. The large-scale structure of the universe is a delicate and beautiful tapestry, woven from the threads of the initial quantum fluctuations and shaped by the interplay of cosmic expansion, of gravity, and of the other fundamental forces. The discovery of a new force would be like discovering a new and previously unknown thread in this tapestry. It would not just add a new detail to the picture, it would change the entire pattern. And it would give us a new and more powerful tool for understanding the deep, and still mysterious, connection between the quantum world of the very small and the cosmological world of the very large. The connection that is at the heart of the entire, beautiful, and ongoing story of our cosmic home. The evolution of our universe, from the fiery simplicity of the Big Bang to the cool, complex, and structured cosmos we see today, is a story of a progressive breaking of symmetry. In the very first moments of the universe, at the incredibly high energies of the Planck era, it is thought that all the fundamental forces of nature were unified into a single primordial superforce, governed by a single, large, and highly symmetric mathematical group. The universe, in this state, was a perfect, undifferentiated, and featureless whole. But as the universe expanded and cooled, it underwent a series of phase transitions, similar to the way that water vapor, as it cools, condenses into liquid water and then freezes into solid ice. At each of these phase transitions, a part of the primordial symmetry was spontaneously broken, and a new and more complex structure emerged. The first of these phase transitions may have been the one that separated gravity from the other, grand unified force. The next one, at the gut energy scale, would have been the one that broke the grand unified symmetry, causing the strong nuclear force to freeze out as a separate interaction. And the final phase transition, at the electroweak scale, would have been the one that broke the electroweak symmetry, separating the electromagnetic and weak nuclear forces and giving the fundamental particles their mass through the Higgs mechanism. The discovery of a new fundamental force would be a profound new piece of this historical puzzle. It would imply the existence of a new and previously unknown symmetry group in the fundamental laws of nature, a symmetry that is broken at some, as yet unknown, energy scale. The properties of this new force, its strength, Its range, its couplings to the other particles would give us a clue about the nature of this new symmetry and about the energy scale at which it was broken. A new force could also have a profound impact on the evolution of the early universe. The phase transitions that break these fundamental symmetries are not always smooth. Gentle processes. They can be violent, dynamic events, and they can leave behind topological defects. Stable. Remnant structures of the old, more symmetric vacuum state that can persist to the present day. These defects, as we have seen, can be one-dimensional cosmic strings, two-dimensional domain walls, or zero-dimensional monopoles. The existence of a new force, associated with a new broken symmetry, would open up the possibility of a whole new class of these exotic astrophysical objects. The detailed, observational search for these topological defects is a powerful, if indirect, way to probe the physics of the very early universe and to search for the signatures of new, broken symmetries. The evolution of the universe is a story of a progressive unfolding of complexity, a story of how, from a state of perfect and, in a sense, sterile symmetry, all the rich and diverse structures of our world have gradually emerged, and the fundamental forces of nature are the rules that have governed this process of cosmic symmetry breaking. The discovery of a new force would not just be about adding a new rule to the game. It would be about discovering a new and deeper layer of the game itself. A layer that would give us a new and more profound understanding of the beautiful and still mysterious connection between the timeless, mathematical world of symmetry and the dynamic, evolving, and beautifully asymmetric world of our own lived experience. The existence of a new fundamental force could have a profound and transformative impact on our understanding of black holes, those enigmatic and extreme objects that represent the ultimate victory of gravity over all other forces. In our current four-force picture, a black hole is a remarkably simple object, according to the no-hair theorem of general relativity. A stable, astrophysical black hole is completely characterized by just three properties: its mass, its spin, and its electric charge. All the other detailed information about the matter that collapsed to form the black hole is seemingly lost forever behind the event horizon. But a new force could change this simple picture in a number of dramatic ways. If the new force is a long-range force, mediated by a new light and perhaps massless boson, then a black hole could also have a new kind of hair. It could have a charge associated with this new force, and it would be surrounded by a new long-range field. This would mean that a black hole is not as simple as we thought, and it would provide a new and potentially observable way to probe the physics beyond the standard model. We could, in principle, detect the effects of this new long-range field on the orbits of stars and other matter around the black hole. A new force could also have a dramatic impact on the process of Hawking radiation, the quantum mechanical process by which black holes are thought to slowly evaporate. The rate of Hawking radiation and the spectrum of the particles it produces depends on the number and the properties of all the fundamental particles that exist in nature. If there are new particles associated with a new force that are light enough to be produced in the Hawking process, then a black hole would evaporate faster than our standard calculations predict. The detailed thermal spectrum of the Hawking radiation would also be changed. In the very final moments of a black hole's evaporation, when its temperature becomes incredibly high, it would radiate a shower of all the fundamental particles of nature, including the particles of any new hidden sectors. The ability to detect the final explosive burst of a small evaporating primordial black hole would be a powerful and unique window into the full spectrum of fundamental particles and forces. A new force could also play a role in resolving the deep conceptual paradoxes of black hole physics, like the information paradox and the nature of the singularity. Some theories that propose a new, short-range, repulsive force, for example, suggests that this force could become dominant at the incredibly high densities found inside a black hole, preventing the formation of a true infinite singularity and replacing it with a new, exotic, and ultra-dense site of matter. The interplay between gravity and a new force could also be the key to understanding the deep, holographic connection between the geometry of space-time and the quantum information that is stored on the event horizon. The universe of black holes is a universe of extremes, a place where the laws of physics are pushed to their absolute limits. And it is in these extreme and still mysterious environments that the subtle effects of a new, and as yet undiscovered, force of nature may be most clearly and powerfully revealed. The behavior of the fundamental forces in the extreme and exotic environments of the cosmos is a powerful and fascinating probe of the underlying laws of nature. And nowhere are these environments more extreme than in the vicinity of a neutron star. A neutron star is the incredibly dense, city-sized remnant of a massive star that has exploded in a supernova. It is, in essence, a giant atomic nucleus, with a mass of up to twice that of our Sun, compressed into a sphere with a radius of just 10 kilometers. The density of matter in the core of a neutron star is so high that normal atoms cannot exist. The immense pressure has crushed the electrons and the protons together to form a sea of tightly packed neutrons, a state of matter known as neutronium. In this extreme environment, the four fundamental forces of nature behave in ways that are very different from our everyday experience. Gravity, of course, is incredibly strong. The gravitational field at the surface of a neutron star is hundreds of billions of times stronger than that on Earth. This intense gravity warps the fabric of space-time around the star so dramatically that light is visibly bent, and time itself is slowed down. Electromagnetism also plays a crucial and often dramatic role. Neutron stars are born spinning incredibly rapidly, and they have some of the strongest magnetic fields in the entire universe. A magnetar is a particular type of neutron star with a magnetic field that is 1,000 times stronger than that of a normal neutron star. A field so powerful that it can buckle the star's solid crust, creating a starquake and releasing a vast and often destructive burst of gamma rays and X-rays. In this ultra-strong magnetic field, the very vacuum of space is thought to become polarized, a bizarre quantum effect that should affect the way that light propagates. But it is the two nuclear forces, the strong and the weak, that truly dominate the inner world of a neutron star. The strong nuclear force is what provides the primary outward pressure that supports the star against the immense inward crush of gravity. The balance between these two titanic forces is what determines the stability and the ultimate fate of the star. If the star is too massive, even the incredible repulsive pressure of the strong force will not be enough to halt the gravitational collapse, and the neutron star will continue to collapse to form a black hole. The weak nuclear force is also crucial. It is the force that governs the processes of neutron decay and electron capture, processes that determine the detailed composition and the thermal evolution of the star's core. The interior of a neutron star is a deep and mysterious place, a realm where our understanding of nuclear physics is pushed to its absolute limits. We do not know for sure what the state of matter is in the very center of a neutron star. It may be a simple sea of neutrons, or at these incredible densities, the neutrons themselves may break down into a new and even more exotic state of matter, a quark-gluon plasma, the same state that is thought to have existed in the very first moments of the universe's existence. A neutron star is a cosmic laboratory, a place where we can study the behavior of matter and the interplay of the fundamental forces under conditions that we can never hope to replicate on Earth. And it is a place where the subtle effects of a new, and as yet undiscovered, fifth force could be amplified and made manifest. A new force could change the equation of state of the dense nuclear matter, changing the maximum possible mass of a neutron star. It could affect the star's cooling rate or the properties of its magnetic field. By precisely measuring the properties of neutron stars, their masses, their radii, their spin rates, their temperatures, and by comparing these observations with the predictions of our theoretical models, we can place powerful constraints on a wide range of new physics. The study of these extreme and beautiful objects is a powerful and complementary approach in our ongoing, multifaceted quest to discover the full, and perhaps still hidden, set of rules that govern our universe. The quest to understand the behavior of the fundamental forces in the very first moments of the universe's existence is a journey into a realm of almost unimaginable energy, density, and temperature. It is a journey that takes us back to a time before atoms, before nuclei, before even protons and neutrons, to a time when the universe was a hot, dense, and rapidly expanding soup of fundamental particles and forces. To theorize about this primordial era, to build a coherent and predictive model of the Big Bang, is one of the greatest and most profound challenges in all of science. Our primary tools in this endeavor are our two great theoretical frameworks: Einstein's general theory of relativity, which describes the dynamics of the expanding space-time, and the standard model of particle physics, which describes the behavior of the matter and the forces within it. By combining these two theories, we can create a powerful and remarkably successful standard model of cosmology, a model that can trace the evolution of the universe from about 1 microsecond after the Big Bang to the present day. This model successfully explains the expansion of the universe, the existence and the detailed properties of the cosmic microwave background, the primordial abundances of the light elements, and the formation of the large-scale structure of the cosmos. But the standard model is incomplete. It does not explain the origin of the universe itself, the nature of dark matter and dark energy, or the reason for the matter-antimatter asymmetry. And at the very earliest times, in the first infinitesimal fraction of a second, at the incredible energies of the Planck era, our current theories break down completely. This is the realm of quantum gravity, the realm where a new unified theory is needed. To explore these pre-standard model epochs, to try and build a theory of the very beginning, physicists have developed a number of powerful and often speculative theoretical tools. Cosmic inflation, as we have seen, is one of the most important of these. It is a theory that provides a dynamical explanation for the initial conditions of the hot Big Bang, and it makes specific, testable predictions about the properties of the primordial density fluctuations. String theory is another. It is a candidate theory of everything that has the potential to describe the physics of the Planck era and to provide a consistent quantum mechanical description of the universe's origin. Another crucial tool is the use of large-scale computer simulations. By programming the fundamental laws of physics into a powerful supercomputer, we can create a virtual universe in a box. We can set the initial conditions to match those inferred from the cosmic microwave background, and then we can let the simulation evolve for 14 billion years of virtual time, watching as the tiny initial density fluctuations grow under the influence of gravity and the other forces into a complex cosmic web of galaxies and clusters. These simulations are an essential bridge between our theories and our observations. They allow us to test our cosmological models in a detailed and quantitative way, to see if they can reproduce the complex statistical properties of the universe we actually observe. The behavior of the forces during the Big Bang is a story of a progressive unfolding of complexity from a state of primordial simplicity and symmetry. It is a story that is written in the language of theoretical physics, a story that we are slowly and patiently learning to read. And it is a story whose first and most mysterious chapter, the chapter that describes the very moment of creation itself, is still waiting for a final and complete theory to be written. The societal and technological impact of our long human journey of space exploration has been profound, far-reaching, and often unexpected. It is a journey that has not just expanded our knowledge of the cosmos, it has also transformed our world, our technology, our culture, and our very sense of what it means to be human. The most obvious and direct impact has been in the realm of technology. The intense and unforgiving demands of spaceflight have been a powerful driver of innovation in a host of different fields. The need for lightweight, robust, and reliable electronics for our spacecraft led directly to the development of the integrated circuit, the microchip that is now at the heart of our computers, our smartphones, and our entire digital world. The need for new, high-strength, lightweight materials for our rockets and our satellites has led to the development of new metal alloys, of composites, of ceramics, that are now used in everything from airplanes and cars to medical implants and sporting goods. The need to communicate with our robotic emissaries across the vast distances of the solar system has spurred a revolution in telecommunications, leading to the development of the satellite communication technologies that now connect our global village. The need to power our spacecraft in the dark, cold vacuum of space has led to the development of highly efficient solar cells and of long-lived, reliable nuclear power sources. And the need to keep our astronauts alive and healthy in the closed-loop environment of a spacecraft has led to breakthroughs in a host of different fields, from water purification and air recycling to medical monitoring and telemedicine. But the impact of space exploration goes far beyond these practical, technological spin-offs. It has also had a profound and transformative impact on our culture and on our collective human consciousness. The space race of the 1960s, for all its Cold War origins, was a powerful and unifying force. It was a grand human adventure that captured the imagination of the entire world and inspired a generation to pursue careers in science, in technology, in engineering, and in mathematics. The image of the Earth as seen from space, the famous blue marble photograph taken by the crew of Apollo 17, has become one of the most iconic and influential images in all of human history. It is an image that has no borders, no divisions, no signs of the petty, human conflicts that have so often defined our history. It is an image of a single, beautiful, fragile, and interconnected world, a world that we all share, and a world that we all have a responsibility to protect. This overview effect, the profound cognitive shift in awareness that has been reported by so many astronauts, is perhaps the most important and most hopeful. Societal impact of space exploration. It is a perspective that can foster a sense of global unity, of environmental stewardship, and of a shared human destiny. And space exploration continues to be a powerful engine of inspiration and of education. The images from the Hubble Space Telescope, the live feeds from the International Space Station, the daily updates from the rovers on Mars. These are not just scientific data. They are a constant and beautiful reminder of the wonder, the beauty, and the vastness of the universe we inhabit. They are a source of inspiration for a new generation of explorers, of scientists, of dreamers. And they are a powerful antidote to the small-mindedness, the tribalism, and the short-term thinking that so often seem to dominate our world. The journey into space is a journey that has given us not just new technologies, but also a new perspective. And it is this new perspective, this new cosmic consciousness, that may, in the end, be its most valuable and enduring gift to humanity. The discovery of a new, fundamental force of nature would not just be a matter of academic interest. It would be a discovery with the potential to unleash a new wave of transformative technologies. Technologies that could reshape our world in ways that we can currently only begin to imagine. The history of science is a testament to this powerful connection between fundamental discovery and technological revolution. The discovery of the laws of electromagnetism in the 19th century was, at the time, a purely intellectual pursuit, a quest to understand the nature of electricity, of magnetism, and of light. But it was a quest that would, in the span of just a few decades, lead directly to the invention of the electric motor, the generator, the radio, the television, and the entire technological infrastructure of our modern, electrified, and interconnected world. The discovery of the laws of quantum mechanics in the early 20th century was an even more profound and seemingly more abstract revolution, but it was a revolution that would lead directly to the invention of the transistor, the laser, the computer, and the entire digital age in which we are now living. What new technologies might a new force enable? The answer, of course, depends on the specific properties of the force, its strength, its range, its couplings to the other particles. But we can allow ourselves to speculate. If the new force is a long-range force, it could lead to new forms of communication, of energy transmission, or even of propulsion. If it is a short-range force, it could lead to new ways of manipulating matter at the atomic and nuclear level, with potential applications in material science, in medicine, and in energy production. If the new force is a dark force that communicates between our world and the world of dark matter, it could, in the far future, give us a way to see and to interact with the invisible, dark sector of the universe. This could lead to new forms of imaging, of sensing, and perhaps even of a new, dark technology. The connection between a new force and the quantum world is particularly intriguing. A new force could be the key to building a large-scale, fault-tolerant quantum computer. The primary challenge in quantum computing is decoherence, the process by which a quantum system loses its delicate, superpositional nature through its interaction with the environment. A new force could provide a new way to control and to shield our quantum bits, or qubits, from this environmental noise, allowing us to build much more powerful and more reliable quantum computers. And a quantum computer, in turn, could be a powerful tool for understanding the properties of the new force, a beautiful positive feedback loop between fundamental discovery and technological innovation in the realm of energy. A new force could open up completely new possibilities. Our current nuclear energy technologies, both fission and fusion, are based on our understanding of the strong and weak nuclear forces. A new force, with its own unique properties, could lead to new, and perhaps even more efficient, ways of releasing the immense energy that is stored in the heart of the atom. The journey from a fundamental discovery in physics to a transformative, world-changing technology is often a long, winding, and unpredictable one. It can take decades, or even centuries, and it requires a sustained and patient investment in basic, curiosity-driven research. The kind of research that is not aimed at a specific, short-term application, but is driven by the simple and powerful desire to understand the world at its deepest level. But it is a journey that is, in the end, one of the primary engines of human progress. And the discovery of a new, fundamental force of nature would be a moment that would not just ignite a new era of scientific discovery, but would also, almost certainly, plant the seeds for a new, and currently unimaginable, technological future. The future of our exploration of the cosmos, the missions that will be launched in the coming decades and centuries, will be shaped by the powerful and synergistic interplay of our evolving scientific questions and our ever-advancing technological capabilities. The questions we ask of the universe are becoming more profound, more ambitious, and more focused. And the tools we are building to answer these questions are becoming more powerful, more sensitive, and more intelligent. In the near term, in the coming decade, we will see a new wave of flagship missions that will build on the legacy of Hubble and the other great observatories. The James Webb Space Telescope is already revolutionizing our view of the infrared universe, and it will be joined by the Nancy Grace Roman Space Telescope, a wide-field survey telescope that will map the distribution of dark matter and dark energy with unprecedented precision, and that will use its coronagraph to directly image large, Jupiter-like planets around nearby stars. On the ground, a new generation of giant. 30-meter class optical telescopes will provide a powerful synergy with these space-based observatories, allowing for the detailed, high-resolution follow-up of the most interesting objects they discover. The search for life beyond Earth will move from a process of simply detecting exoplanets to a process of characterizing their atmospheres. The techniques of transit spectroscopy, which Webb is pioneering, will be refined and scaled up, with the ultimate goal of building a future. Large, space-based telescope that is specifically designed to search for the chemical biosignatures of life in the atmospheres of dozens of nearby, Earth-like worlds. This would be a mission of profound, and perhaps civilization-changing, significance. The exploration of our own solar system will also enter a new and exciting phase. We will return to the moon, not just for brief, Apollo-style visits, but to stay. The Artemis program, a new international collaboration, will establish a permanent human research outpost on the lunar surface. A base camp that will serve as a testbed for the technologies and the operational strategies that we will need for the much longer and more challenging journey to Mars. The robotic exploration of the outer solar system will continue, with missions to the ice giants, Uranus and Neptune, and a new focus on the ocean worlds of Jupiter and Saturn, a future mission to Enceladus. For example, could fly through the plumes of water that are erupting from its south pole and sample them directly, searching for the organic molecules and the other chemical signs of a potential subsurface biosphere. Looking further into the future, the development of new, advanced propulsion technologies, like nuclear thermal and, eventually, nuclear fusion, will be the key to unlocking a new era of human exploration. These technologies will make a human mission to Mars a routine and sustainable enterprise, and they will open up the entire solar system to a new level of rapid and intensive exploration. And on the very longest timescales, on the timescale of centuries and millennia, the dream of interstellar travel may one day move from the realm of science fiction to the realm of engineering. The development of a fusion-powered world ship or a beam-powered relativistic probe would be a project of almost unimaginable complexity and scale. But it is a project that is not forbidden by the known laws of physics. It is a project that is, in principle, possible. The future of space exploration is a future of ever-expanding horizons, a future where each new discovery, each new technology opens up a new set of questions, a new set of possibilities, a new frontier to explore. It is a journey that is driven by our deepest and most noble human impulse, the desire to understand, to explore, and to reach for the stars. And it is a journey that is, in the end, not just about the cosmos, but about ourselves, about our own limitless potential for growth, for discovery, and for a future that is as vast and as wonderful as the universe itself. The search for new fundamental forces is not just a quest to complete our inventory of the cosmos. It is a quest that could provide the key to a deeper, more unified, and more elegant understanding of the laws of nature. It is a quest that is driven by the deep and almost aesthetic belief that the universe, at its most fundamental level, is simple and beautiful. And one of the most powerful and beautiful ideas in this quest is the idea of symmetry. Symmetry is a concept that we are all intuitively familiar with. A sphere is symmetric because it looks the same no matter how you rotate it. A snowflake is symmetric because it has a beautiful six-fold rotational symmetry. In physics, a symmetry is a transformation that you can perform on a system that leaves its fundamental properties, its laws of physics, unchanged. And a profound and beautiful theorem, Noether's theorem, tells us that for every continuous symmetry in nature, there is a corresponding conserved quantity. The fact that the laws of physics are the same today as they were yesterday A symmetry in time translation leads to the conservation of energy. The fact that the laws of physics are the same here as they are on the other side of the galaxy. A symmetry in space translation leads to the conservation of momentum. The symmetries of nature are not just a matter of aesthetic beauty. They are the deep, underlying source of the conservation laws that govern our universe. The forces of the Standard Model are also based on a kind of symmetry, a more abstract, internal symmetry called a gauge symmetry. The theory of electromagnetism, for example, is based on a simple U-gauge symmetry, say, and the requirement that the laws of physics be invariant under this symmetry. Transformation naturally and inevitably leads to the existence of the electromagnetic force and its force-carrying particle, the photon. The electroweak theory is based on a larger SU-XU symmetry group, and the strong nuclear force is based on an even larger SU symmetry group. The quest for a grand unified theory is, in essence, a search for a single, even larger symmetry group that contains all three of these, a group like SU or SO. The discovery of a new fundamental force would be a direct and powerful clue about the existence of a new and previously unknown gauge symmetry in the laws of nature. By studying the properties of this new force, we could begin to deduce the mathematical structure of this new symmetry group, and to understand how it fits into the larger, and perhaps unified, picture of all the forces. The breaking of these symmetries is as important as the symmetries themselves. As we have seen, the universe, as it cooled after the Big Bang, is thought to have undergone a series of spontaneous symmetry-breaking phase transitions. The Higgs mechanism is the most famous example of this. At high energies, the universe was in a symmetric, electroweak state. But as the universe cooled, the Higgs field condensed into a particular vacuum state, a process that broke the electroweak symmetry and gave mass to the W and Z bosons, while leaving the photon massless. This process of symmetry breaking is what gives rise to the rich and complex structure of the world we see. The search for a new force is, in this sense, a search for the history of cosmic symmetry breaking. It is a form of cosmic archaeology, a quest to uncover the fossilized remnants of the more symmetric and more unified state of the very early universe. The symmetries of nature are the deep and often hidden source of the order, the beauty and the mathematical elegance of the physical world, and the quest to discover new forces and the new symmetries from which they arise is a quest to read the very mind of God, to understand the single, beautiful, and unified thought that is the source of our entire, vast, and wonderful cosmos. The public's fascination with the mysteries of the universe is a deep and often untapped well of curiosity and wonder. But the language of modern physics, with its abstract mathematics and its counterintuitive concepts, can often seem like an impenetrable barrier, a secret code that is accessible only to a small, initiated priesthood of professional scientists. Bridging this gap, translating the profound and beautiful ideas of fundamental physics into a language that is accessible, engaging, and meaningful to a wider audience is one of the most important and challenging tasks for the scientific community today. One of the most effective strategies for doing this is to connect the abstract concepts of physics to the concrete, lived experiences of our everyday lives. The laws of thermodynamics, for example, can be explained not just with equations, but with the familiar experience of a cooling cup of coffee. The curvature of space-time can be visualized with the analogy of a bowling ball on a rubber sheet. And the strange quantum world of superposition and uncertainty can be made more tangible, if not fully intuitive, through its powerful and resonant metaphors with the nature of our own consciousness. With the experience of sleep and of dreams, storytelling is another powerful tool. The history of science is not a dry, linear progression of facts and theories. It is a rich and dramatic human story. A story of brilliant and often flawed individuals, of intense rivalries and deep collaborations, of moments of sudden, breathtaking insight, and of long, patient years of hard, meticulous work. By telling these stories, by putting a human face on the abstract enterprise of science, we can make the process of discovery more relatable, more inspiring, and more deeply human. The visual medium, in all its forms, is also a crucial part of this effort. The breathtaking images from the Hubble Space Telescope have done more to capture the public's imagination and to inspire a sense of cosmic awe than 1,000 scientific papers. The beautiful and intuitive animations that can be created with modern computer graphics can make the invisible world of quantum fields or the vast four-dimensional landscape of space-time visible and almost tangible. The rise of new media platforms, from YouTube and podcasts to social media and virtual reality, has created a new and powerful ecosystem for science communication. These platforms allow scientists to speak directly to the public, to share their passion and their excitement, and to engage in a real and often lively two-way dialogue. This is a powerful way to break down the traditional barriers between the experts and the laity, and to foster a more democratic and participatory culture of science. And finally, there is the crucial role of hands-on, experiential learning, science festivals, museum exhibits, citizen science projects. These are all ways to give people a direct, personal experience of the process of scientific discovery. To look through a telescope and to see the rings of Saturn for yourself. To participate in the search for new pulsars by analyzing radio astronomy data on your own computer. These are experiences that can ignite a lifelong passion for science and for the universe. The quest to understand the fundamental laws of nature is not a journey for a small, elite group of specialists. It is a shared human adventure, an adventure that speaks to our deepest and most ancient questions about who we are, where we came from, and what our place is in the grand and cosmic scheme of things. And by finding new and more creative ways to share the stories, the beauty, and the wonder of this journey, we can invite all of humanity to participate in this great and ongoing conversation with the cosmos.